Settle in now. Let the weight of the day begin to release its hold, gently, piece by piece. There is nothing you need to do, nothing you need to solve. All that is asked of you in this moment is to breathe. Feel the air as it enters, cool and quiet, and as it leaves, warm and slow. Notice the subtle shift in the fabric of your clothes with each breath, the gentle pressure of the surface beneath you, holding you completely. This is a space for quiet curiosity, a place where questions can unfold without the need for immediate answers. Tonight, we are not here to argue or to prove, but simply to wonder, to drift on the currents of a single, elegant question that has echoed in the minds of children and scientists alike, a question that rearranges the very furniture of our world. It's a question about time, about chance, and about the deep, branching pathways of life itself. What if it had been different? What if the dice of cosmic fortune had rolled another way? The sky above a world 66 million years ago was unaware of its own story. It held no knowledge of the future, no inkling of the silence that was to come. It simply was. And in the forests and plains below, life in all its magnificent, sprawling complexity carried on. Great herds moved like living rivers across the land, their footsteps a rhythm that had pulsed for ages. Hunters, honed by millions of years of evolution, moved with a lethal grace through the undergrowth. In the quiet moments, small, furred creatures scurried in the shadows, their hearts beating fast, their world defined by the giants who walked in the sun. It was a world complete, a world that was not waiting for us. It was not a prelude, it was the main act. And then, a change, a moment of impossible energy, a scar left upon the planet that would alter the course of everything that followed. An ending and a beginning, but tonight we will gently set that moment aside. We will imagine a world where that day was just another day, where the light from a distant star did not resolve into a point of incandescent fury, where the sky remained unbroken, and the great rhythm of the Mesozoic era continued its slow, powerful beat. Tonight, we are going to ask, together in this quiet space, what if the dinosaurs never went extinct? Let that question hang in the air for a moment. Feel its shape. It's not a question of monsters and mayhem, not a story of survival in a hostile world. It is a deeper, more thoughtful inquiry. It's a question about how a planet breathes, how life creates and recreates the world it inhabits. It asks what happens when the dominant chord in nature's symphony is never silenced, when it is allowed to evolve and change and branch out over 66 million more years. What kind of world would we find? What would the forests sound like? What color would the sky be, filtered through an atmosphere shaped by a different biology? What would have become of those small, frightened creatures in the undergrowth? And, perhaps most profoundly, where would we be in all of it? This is our journey for tonight. A slow, gentle exploration of a world that might have been. A world without us, but not a world without intelligence, or complexity, or beauty. So let your mind drift. Let the boundaries of the known world soften. We are simply opening a door to a different timeline and peering through, with quiet respect and boundless curiosity. There is no rush. Time, after all, is the one thing we have in abundance on this journey, millions upon millions of years waiting to be explored, one slow breath at a time. Before we step through that door, let's agree on how we'll travel. This is not a journey of absolute certainty. It cannot be. The timeline we are about to explore is a ghost, a phantom path that exists only in the careful latticework of scientific inference and disciplined imagination. So we must be gentle with our conclusions. We are not building a world of facts, but rather a world of plausibility. Think of it as a form of modeling, like the way a meteorologist builds a simulation to understand a storm. They input the known variables, temperature, pressure, humidity, and let the laws of physics sketch out a possible future. Our variables are different. They are ecological pressures, evolutionary trends, geological certainties, and the beautiful, unpredictable chaos of life itself. We will take what we know about the late Cretaceous period, its climate, its continents, its incredible diversity of life, and we will remove one single catastrophic variable, the Chicxulub impactor. With that single change, we will let the simulation run forward, moment by moment, millennium by millennium, for 66 million years. Our guide will be the principles of biology and geology, the fundamental rules that seem to govern how life and planets evolve together. But we must also hold a space for humility. Evolution is not a straight line. It is a riotously branching tree, full of dead ends, surprising innovations, and events of pure dumb luck. We cannot know for certain which branch would have flourished and which would have withered. So when we speak of what would have happened, we are really speaking in the language of might have, of could have, of what the evidence suggests is a strong possibility. We are exploring one of many possible worlds that could have spun out from that single point of divergence. We are not seeking the one true answer because one does not exist. We are here to explore the potential. Our method, then, will be one of careful inquiry. We will look at the creatures of that time not as finished products, but as works in progress. The Tyrannosaurus, the Triceratops, the Ankylosaurus, they were not the end of their lines. They were simply the latest models, perfectly adapted for their world, but with lineages stretching back millions of years and the potential for millions more ahead of them. We will ask, what were the trends already in motion? Brains were getting larger in some groups. Social behaviors were becoming more complex. Herbivores and plants were locked in an ever more sophisticated arms race. We will take these trends and gently extrapolate them, letting them play out across a changing planetary stage. Continents will still drift, mountains will still rise, ice ages will still come and go. These are the geologic drumbeats that our alternative world must march to. The dinosaurs, had they survived, would not have remained the same. They would have had to adapt or perish just like any other form of life. And in that adaptation, in that long, slow dance with a changing Earth, a new world would have been born. So let go of the idea of a static, monstrous world frozen in time. Instead, picture a dynamic, evolving planet, a place of immense biological creativity. This is our primary guardrail. We are not building a theme park. We are attempting to understand an ecosystem on its own terms, an ecosystem given the gift of uninterrupted time. We will proceed slowly, piece by piece, looking at the ripple effects of this one great what-if. We'll start with the most immediate consequences, the survival of the dinosaurs themselves and the suppression of the mammals. Then we will widen our lens, looking at plants, at the climate, at the very chemistry of the air and oceans. We will see how these systems are all connected, how the fate of a single species can echo through the entire planetary system. This is a story of connections, of feedbacks, of a world weaving itself into existence over an immense gulf of time. There is no destination, no final reveal. The journey itself is the purpose. The act of wondering, of seeing our own world made strange and new by imagining its alternative, is where the value lies. So, as we begin, let's hold this thought. We are guests in this imaginary world. We walk with a light step. We observe with an open mind. And we honor the complexity of what we find. Let's begin where you are, right now, in this room. Take a moment to feel the space around you. Is there a faint coolness in the air, a whisper from a window left slightly ajar? Or is there a deep, encompassing stillness, the kind that settles over a house late at night? Notice the quality of the light, even if your eyes are closed. Perhaps it's the soft, ambient glow of a street lamp filtering through the curtains, painting a faint pattern on the ceiling. Or maybe it's the profound velvet dark of a rural night, a blackness so complete it feels like a substance. Listen. Listen past the sounds of this recording. What is the unique auditory signature of your space? Is it the gentle hum of an appliance, a refrigerator cycling on and off. The distant rumble of traffic, softened by distance into a low, continuous murmur. The creak of a floorboard in another room as the house settles. These are the grounding details of your present moment. Now, bring your awareness to the feel of the materials closest to you, the texture of the sheet or blanket against your skin. Is it smooth, perhaps slightly cool to the touch? Or is it a soft, textured fabric like cotton or wool, holding a little of your own warmth? Feel the weight of it, a gentle, reassuring pressure that anchors you to the here and now. Feel the pillow or cushion beneath your head, how it conforms to your shape, supporting you. This is your anchor point. This sensory present, this immediate reality of air, light, sound, and texture. This is where we are. From this point of safety and stillness, we can begin our journey outward and backward into time. Think for a moment about the floor beneath you. Whether it's wood or carpet or tile, it is resting upon a foundation. That foundation rests upon the earth, and that earth, that small patch of planet right beneath you, is a library. It is an archive of unimaginable depth. If you could drill down, straight down from where you are now, you would pass through layers of soil, then clay, then rock. Each layer is a page from a book, written in a language of sediment and stone. You would pass through the story of the last few thousand years, the time of human history. Then you would go deeper, past the records of the last ice age, when this very spot might have been buried under a mile of ice, or perhaps was a wind-swept tundra or a savanna teeming with mammoths and giant sloths. Deeper still, you enter the age of mammals, the Cenozoic. The layers of rock speak of climates warmer than our own, of forests in places that are now deserts, of strange and wonderful beasts that rose and fell long before our own ancestors took their first upright steps. And if you kept going, deeper and deeper, you would eventually cross a boundary, a thin, dark line in the rock, found all over the world. It's a layer of iridium-rich clay, the faint chemical echo of a 6-mile-wide asteroid striking the Earth. This is the K-Page boundary, the tombstone of an age. Below that line, everything is different. Below that line, you are in the Mesozoic, the age of dinosaurs. The very ground beneath you holds this story. It is not an abstract concept from a book. It is a physical reality, a vertical timeline stretching down into the cool, quiet dark of the Earth's crust. Tonight, we are simply imagining a world where that thin, dark line of iridium was never laid down. A world where the geological chapter of the Cretaceous did not end so abruptly, but instead flowed seamlessly into the next, carrying its incredible inhabitants along with it. The continents would still be drifting, the mountains still rising, but the story written upon them would be entirely different. So, as you rest here in your room, feeling the air on your skin, feel that connection, that thread of physical continuity that ties you in this moment to that ancient world. The atoms in the air you are breathing are the same atoms that were cycled through the lungs of a velociraptor. The water in your body once fell as rain on the vast fern prairies of the Cretaceous. You are made of the same planetary stuff, and by feeling that connection we make the past present and we make the imaginary feel just a little more real. Why does this question matter? Why spend our quiet hours contemplating a world that never was? On one level, it is simply a grand and wonderful exercise in imagination, a way to stretch our minds beyond the familiar. But if we look closer, we find that asking what if about the past is also a profound way of understanding the present. It helps us see the hidden architecture of our own world, the deep causal chains that brought us to this very moment, lying here, listening to these words. The absence of the dinosaurs is not a neutral fact about our planet. It is arguably the single most important precondition for the world as we know it. Their extinction was the Great Clearing, the event that swept the board clean for a new set of players to emerge from the wings. Without that event, the story of the last 66 million years would not just be different, it would be unrecognizable. Consider the mammals. For over 150 million years, while the dinosaurs reigned, mammals existed. They were successful, diverse, and widespread, but they were small. They lived in the cracks of the world, in the shadows, in the night. Their evolutionary potential was capped by the sheer ecological dominance of the dinosaurs. There were no large mammalian herbivores because dinosaurs like the hadrosaurs and ceratopsians filled those roles with crushing efficiency. There were no large mammalian predators because the tyrannosaurs and their kin were the undisputed masters of that domain. The extinction event was a release. It was like a dam breaking. Suddenly, a planet full of empty ecological niches was laid bare, and the mammals, with their warm-blooded metabolism, their adaptability, their maternal care, were perfectly positioned to rush in and fill the void. Within just a few million years, a geological eye blink, they exploded in size and diversity. The age of mammals was born directly from the ashes of the age of dinosaurs, and from one branch of that explosive mammalian radiation, the primates, a path eventually led to us. So when we ask what the world would be like if the dinosaurs had survived, we are simultaneously asking what the world would be like if the age of mammals had never happened. And that forces us to confront a rather humbling thought. Our own existence is not the grand finale of a long, purposeful march of progress. It is the result of a cosmic accident. We are here because they are not. This question then peels back the veneer of inevitability from our own world. It shows us that the way things are is not the only way they could have been. The world is not a machine designed to produce humans. It is a chaotic, creative system that has stumbled upon countless forms of being, and ours is just one, born of a particular set of historical contingencies. This perspective shifts our place in the grand scheme of things. It moves us from the center of the story to just one of many possible outcomes. There is a deep and quiet wisdom in that shift. It fosters a sense of humility and a greater appreciation for the sheer, contingent luck of our existence. It also helps us understand the nature of ecosystems on a planetary scale. By imagining a world with a different biological foundation, we can start to see how life shapes the planet itself. The types of plants that grow, the chemistry of the atmosphere, the rate of erosion, all of these things are tied to the dominant forms of life. A world of giant dinosaurs would have a different global metabolism than our world of mammals. Its forests would be structured differently, its soils would have a different composition. By studying this ghost world, we learn about the powerful feedback loops that connect biology and geology in our own. So this is not just an escape into fantasy. It is a tool for understanding. It is a way of seeing the familiar world with new eyes, of appreciating the deep, hidden history that underpins every landscape, every creature, every breath we take. The stakes are not about a hypothetical past. They are about a deeper perception of the real present. As we move forward on this journey, there are a few threads we will begin to plait together. Think of them as signposts, recurring themes that we will revisit from different angles as our picture of this alternate Earth becomes richer and more detailed. We will not resolve them immediately. Instead, we will let them linger, gathering depth and meaning as we go. The first thread is the question of intelligence. When we imagine a world where dinosaurs continued to evolve, it is almost impossible not to wonder, would they have become intelligent in the way that we understand it? We see hints of it in the fossil record. Certain small predatory dinosaurs, like the troodontids, had unusually large brains for their body size, comparable to modern birds. They had grasping hands and large, forward-facing eyes, suggesting a sophisticated sensory world. If their lineage had continued for another 66 million years, what might have emerged? We will explore this possibility not as a certainty, but as a fascinating potential. We will return to the idea of the dinosauroid, the hypothetical sapient dinosaur, and consider what such a being might be like and how its existence would have shaped the planet. A second thread we will follow is the rise of a new kingdom of plants, grass. Grasslands are a relatively recent innovation on Earth. They began to spread in the Cenozoic, in the wake of the dinosaurs driven by a cooling, drying climate. They co-evolved with the new mammalian herbivores, creating the great savanna ecosystems we know today. But what would have happened if the dominant herbivores were not bison and antelope, but herds of advanced ceratopsians and hadrosaurs? How would these immense creatures have adapted to this new, tough, low-lying food source? Would grasslands have been able to spread at all against the pressure of such different grazers? The story of grass is the story of the second half of the Cenozoic. We will have to ask how that story changes when the main characters are reptilian, not mammalian. And a third thread, perhaps the most subtle, is the thread of sound. Our world is filled with the sounds of mammals, the howl of a wolf, the song of a whale, the chatter of monkeys, the symphony of human language. What would a world without those sounds be like? The soundscape of the Mesozoic would have been profoundly different. The insects, the amphibians, the birds, and of course the dinosaurs themselves would have created a rich and complex acoustic environment. We will try to imagine that soundscape and how it might have evolved over millions of years. What new calls, what new songs, what new forms of communication might have arisen in a world where the dominant voices were never silenced? So keep these three threads in mind as we proceed: the potential for a different kind of intelligence, the challenge of a new kind of botany, and the echo of a lost soundscape. We will pick them up and examine them more closely later. For now, let them be gentle promises of the mysteries still to come. To build our alternate world, we need a shared set of tools, a common language. Let's take a moment to define a few key ideas, not with rigid scientific jargon, but with simple, working descriptions that we can use on our journey tonight. First, when we say dinosaur, what do we actually mean? The word often conjures up a specific image, perhaps of a Tyrannosaurus or a Brontosaurus. But the dinosaurs were an incredibly diverse group of animals that dominated the Earth for nearly 200 million years. For our purposes, when we say dinosaurs, we are primarily talking about the non-avian dinosaurs. That is, all the dinosaurs except for the branch that eventually evolved into birds. So in our thought experiment, birds still exist. They are, after all, a living lineage of dinosaurs. Our focus is on the survival of the other great groups, the sauropods, those long-necked giants, the theropods, the bipedal carnivores like T-Rex and Allosaurus, the ornithischians, a vast group of herbivores that includes the armored ankylosaurs, the horned ceratopsians, and the duck-billed hadrosaurs. These are the groups that were wiped out by the extinction event, and these are the groups we are bringing back. Our first assumption, our point of divergence, is that the Chicxulub asteroid impact either did not happen or was significantly less severe, such that it did not cause a global mass extinction. The massive volcanic activity in India, the Deccan Traps, was also happening around this time and causing climate stress. We will assume that without the knockout blow from the asteroid, the world's ecosystems, though stressed, would have recovered and continued, with dinosaurs remaining the dominant terrestrial vertebrates. Next, let's talk about evolution. It is not a ladder of progress leading to a predetermined goal. It is not a process of things getting better. It is simply a process of adaptation to changing local conditions. Organisms with traits that are well suited to their environment are more likely to survive and reproduce, passing those traits on. Over deep time, this process of natural selection can lead to profound changes. So, when we imagine 66 million more years of dinosaur evolution, we are not imagining them becoming ever larger or more monstrous. We are imagining them adapting to the real geological and climatic changes that we know happened during that time: the cooling of the planet, the separation of continents, the rise of new types of plants. And finally, let's define the timescale we are working with. 66 million years is a stretch of time that is almost impossible for the human mind to grasp. Human civilization is only about 10,000 years old. The entire existence of our species, Homo sapiens, is around 300,000 years, so the time we are talking about is more than 200 times longer than the entire history of humanity. We cannot think about this in terms of single lifetimes or even centuries. We must think in terms of deep time. We must imagine change happening at a geological pace, slow, relentless, and transformative. When we talk about a new species evolving or a climate shifting, these are processes that unfold over hundreds of thousands or millions of years. So we will be zooming in and out from the scale of a single creature living its life in a prehistoric forest to the vast planetary scale of continents drifting and mountains rising over eons. With these working definitions in hand of the dinosaurs we are saving, the nature of the extinction event we are avoiding, the process of evolution as adaptation, and the immense scale of deep time, we have our basic toolkit. We can now begin to construct our world, not from fantasy, but from a foundation of plausible scientific what-ifs. To understand where we are going, we must first have a clear picture of where we are starting from. Let's paint a brief portrait of the world as it was 66 million years ago, in the final moments of the geological period known as the Cretaceous. Forget the popular image of a gloomy, primitive swamp world. The late Cretaceous was a vibrant, dynamic, and in many ways very modern planet. The continents were beginning to look something like their present-day configurations, although they were not in the same places. North America was split in two by a great inland sea, the Western Interior Seaway, that ran from the Arctic to the Gulf of Mexico. South America, Africa, Australia, and Antarctica were all drifting apart from their previous connections. India was an island continent, racing northwards on a collision course with Asia. This planetary geography created a world that was, on average, much warmer than our own. There were no polar ice caps. Forests of a kind we would find strange and beautiful grew all the way to the poles. In the high Arctic, dinosaurs like the pygmy tyrannosaur, Nanuqsaurus, and the hadrosaur Ugrunnaluk lived through months of winter darkness in vast coniferous forests. The climate was generally more humid and tropical. The world was a greenhouse, not an ice house. The plant life was also a mix of the familiar and the alien. Ferns, cycads, and conifers were still abundant, but a revolutionary new type of plant had recently taken over the world, the flowering plants or angiosperms. They had evolved a brilliant new strategy for reproduction, using flowers to attract insects and other animals as pollinators and fruits to entice them into spreading their seeds. By the end of the Cretaceous, they had become the dominant form of plant life, creating new types of forests with dense, leafy canopies. The world was becoming more colorful, more full of scent, more interconnected. And into this world walked the dinosaurs. They were at the peak of their diversity and sophistication. In North America, vast herds of Triceratops and the duck-billed Edmontosaurus browsed on the lush vegetation, stalked by the ultimate apex predator, Tyrannosaurus rex. These were not sluggish, stupid monsters. They were highly evolved animals with complex behaviors. Fossil evidence suggests many hadrosaurs lived in herds and cared for their young in nesting colonies. The horned ceratopsians likely engaged in complex social displays and ritual combat with their elaborate horns and frills. The T-Rex itself was not just a brute. It had a large brain with huge olfactory bulbs, suggesting an incredible sense of smell, and its eyes were positioned for excellent binocular vision. It was a sophisticated hunter in a world of sophisticated prey. And this was just one ecosystem. In South America, long-necked titanosaurs, the last of the mighty sauropods, still strode across the landscape, preyed upon by giant carnivores like Carnotaurus. In Asia, strange theropods like the bizarre, long-clawed Therizinosaurus and the ostrich-like Gallimimus roamed. And everywhere there were the smaller dinosaurs, the raptors or dromaeosaurs like Deinonychus, feathered, intelligent, pack-hunting predators that were a world away from the lumbering giants. And let us not forget the other inhabitants. In the skies, the pterosaurs, those flying reptiles, were still masters of the air, with giants like Quetzalcoatlus, with a wingspan the size of a small airplane, soaring over the inland seas. The oceans teemed with life, including the giant marine reptiles like the mosasaurs, fearsome aquatic lizards that were the top predators of the seas. And, of course, there were the mammals, tiny, shrew-like creatures for the most part, living nocturnal lives, hunting insects in the leaf litter, their entire existence predicated on staying out of the way of the dinosaurs. This was not a world in decline. It was a world at the height of its powers, a stable, complex, and incredibly successful ecosystem that had been running for millions of years. This is our starting point. This is the world that was lost. And this is the world we will now allow to continue its journey, uninterrupted, into the future. Let's begin our exploration by looking at a pattern that is deeply familiar to us, something on a human scale. Think about the relationship between a predator and its prey. It's a concept we understand intuitively. A lion and a zebra on the Serengeti, a wolf and a deer in a northern forest. We often see this as a one-way street. The predator hunts, the prey flees. But over evolutionary time, it is a conversation, a deadly, high-stakes arms race that shapes both participants in profound ways. Let's take a specific example from our own Cenozoic era, the one that happened in our timeline. Look at the evolution of horses and the evolution of wolves. Early horses were small, multi-toed creatures living in forests. As the climate cooled and grasslands spread, they moved out into the open. In this new environment, their predators, early canids, could see them from a long way off. The horses that survived were the ones that could run faster and longer. Over millions of years, this selective pressure drove incredible changes. Their legs grew longer. Their side toes shrank and fused, leaving a single, powerful hoof, perfect for running on hard ground. Their teeth changed to grind the tough, silica-rich grasses. They became larger, more powerful, and developed the stamina to outrun their pursuers. But the wolves were not standing still. The horses that were easier to catch were weeded out, so the wolves that survived were the ones that were smarter, faster, and better at hunting as a team. They developed social structures, communication, and incredible endurance. The horse got faster because of the wolf, and the wolf got smarter because of the horse. This is a classic co-evolutionary arms race. Each side is constantly adapting to the innovations of the other. It is a feedback loop that drives both lineages towards greater and greater levels of sophistication. Now, let's apply this same principle to our alternate world. Take the relationship between a tyrannosaur and a triceratops. By the end of the Cretaceous, this was already a highly refined arms race. The tyrannosaur had evolved its bone-crushing bite, its powerful legs, and its keen senses to hunt large, dangerous prey. The Triceratops, in turn, had evolved its massive three-horned skull and its bony neck frill as a formidable defense. Fossil records show tyrannosaur bite marks on Triceratops skulls, some of which healed, proving that these battles happened and the prey sometimes won. So what happens when we let this arms race run for another 10, 20, or 50 million years? The climate is changing. The lush Cretaceous forests are slowly giving way in some places to more open woodlands and eventually perhaps to vast fern prairies or grasslands. The environment is changing the terms of the engagement. In a more open landscape, speed and endurance become more important. Perhaps we would see the tyrannosaur lineage evolve in a direction of greater cursoriality, becoming leaner, longer-legged, better adapted for pursuit. Their descendants might not be the same lumbering giants, but something more akin to a reptilian cheetah, trading brute force for speed. But the Triceratops lineage would have to respond. Perhaps they would become faster themselves, or perhaps they would double down on defense, evolving even larger, more elaborate horns and frills. Maybe their social behavior would become more complex. We see evidence of herding in some ceratopsians. Imagine a herd of advanced 60-million-year-old Triceratops descendants forming a defensive circle around their young, a fortress of horns and shields, a behavior seen in modern musk oxen. The predators would then need to evolve greater intelligence and pack-hunting strategies to break that defense. This is the engine of change, playing out at a scale we can understand. The hunter shapes the hunted, and the hunted shapes the hunter. This isn't just about two species, it's about the whole ecosystem. The evolution of these giants would shape the plants they ate, the smaller animals that lived in their shadow, and the very landscape they moved through. A herd of 10-ton herbivores has a profound impact on its environment. By applying this simple, observable pattern, the coevolutionary arms race, to the inhabitants of the late Cretaceous, we can start to see how a world without the extinction event would not be a static museum of old species. It would be a cauldron of continuous, dynamic, and creative evolution. And it leaves us with a question. If this constant pressure for greater speed, better defenses, and smarter strategies continued for 66 million years, what would be the ultimate result? What kind of creatures, what kind of minds would be forged in that relentless fire? The idea of a co-evolutionary arms race is a powerful tool for imagining new creatures. But what are the limits, what are the boundaries and edge cases that this model runs into? We can't just assume that these trends would continue in a straight line forever. There are physical and biological constraints that shape the path of evolution. Let's stay with our example of the Tyrannosaur-Triceratops dynamic. We imagined a future where tyrannosaurs become faster and leaner, but there's a limit to how large a bipedal animal can be and still be fast. The physics of biomechanics come into play. The stresses on bones and joints increase exponentially with size. An animal the size of a T-Rex is already pushing the limits of what is possible for a two-legged runner. To become significantly faster, it would likely have to become smaller. So instead of a 50-foot-long reptilian cheetah, perhaps the future of the tyrannosaur lineage would be a diversity of forms. Some might remain large, ambush predators in forested environments. Others might shrink, becoming wolf-sized pack hunters on the open plains, sacrificing individual power for group coordination and speed. This is a more realistic evolutionary outcome, not a single, linear progression, but a radiation into multiple new niches. Now consider the Triceratops. We imagined it doubling down on defense, but there are costs to this strategy as well. Growing a massive, bony frill and huge horns requires a tremendous amount of energy and resources, primarily calcium. An animal that invests this heavily in armor is investing less in other things like speed or a larger brain. There's a trade-off. At some point, the defensive structures could become so large and cumbersome that they become a liability, a concept known as maladaptation. Evolution doesn't have foresight. A trait that is advantageous in one environment can become a burden in another. So, the path of the ceratopsians would be a delicate balancing act, constantly negotiating the trade-offs between defense, mobility, and metabolic cost, all against the backdrop of a changing climate and evolving predators. There is also the possibility of a stable state being reached. An arms race doesn't have to go on forever. Sometimes a kind of equilibrium is achieved, where the predator is just successful enough to survive, and the prey is just elusive or well defended enough to survive. The selective pressure then lessens, and both lineages might remain relatively unchanged for millions of years, as long as the environment remains stable. This is a phenomenon known as stabilizing selection. So it's possible that in some parts of our alternate world, creatures very much like a T-Rex and a Triceratops could still be roaming the landscape 66 million years later, finely tuned to each other and their environment, living fossils from a bygone age. This introduces a crucial element of nuance into our thinking. We must avoid the trap of hyper-evolution, of assuming that everything would become fantastically advanced and bizarre. Much of evolution is about conservation, about finding a successful strategy and sticking with it. The world we are building would be a mosaic of the ancient and the new. Some lineages might be radically transformed, while others might be echoes of their Cretaceous ancestors. The cadence of evolution is not uniform. It is a rhythm of long periods of stasis punctuated by bursts of rapid change, often driven by environmental upheaval. Therefore, the implications of our simple arms race model become more complex. It's not a single, predictable outcome, but a branching set of possibilities constrained by physics, shaped by trade-offs, and paced by the rhythm of planetary change. It preserves a calm sense of realism in our speculation. Now let's zoom out. From the one-on-one drama of predator and prey, let's widen our view to the scale of entire systems and the feedback loops that regulate them. A planet's climate and biosphere are not separate things. They are a single, deeply interconnected system. Life doesn't just live on Earth. It actively creates and maintains the conditions for its own survival. This is the core idea of Gaia theory, and while it can be controversial, the basic principle of biogeochemical feedbacks is well established. Think of your own body. You maintain a stable internal temperature of around 98.6 degrees Fahrenheit or 37 degrees Celsius. If you get too hot, you sweat to cool down. If you get too cold, you shiver to generate heat. This is a negative feedback loop. A change in one direction triggers a response that pushes the system back in the opposite direction, maintaining stability or homeostasis. The Earth has similar, though much more complex, feedback loops. One of the most important is the long-term carbon cycle. Volcanoes release carbon dioxide, CO2, into the atmosphere, which acts as a greenhouse gas, warming the planet. But this warming also increases the rate of rock weathering. Rainwater combines with CO2 to form a weak carbonic acid, which dissolves silicate rocks on the continents. The dissolved minerals, including carbon, then wash into the oceans, where marine organisms use them to build their shells. When these organisms die, their shells sink to the ocean floor, eventually forming carbonate rocks like limestone, locking the carbon away in the geosphere. This is a planetary-scale thermostat. If the planet gets too warm from volcanic CO2, weathering speeds up, drawing more CO2 out of the atmosphere, which cools the planet back down. If the planet gets too cold, weathering slows down, allowing volcanic CO2 to build up, which warms the planet back up. This process operates over millions of years, and it has kept Earth's climate within a habitable range for billions of years, despite the sun getting progressively brighter over its lifetime. Now here is the crucial part. Life is deeply involved in this process. The presence of plants on land dramatically accelerates the rate of rock weathering. Their roots break up rocks, and the organic acids they release in the soil enhance chemical erosion. So the biosphere is an active component of the Earth's thermostat. Now let's bring this back to our dinosaur world. The Mesozoic was a greenhouse world with much higher CO2 levels than today. The biosphere was dominated by immense herbivores. Sauropods, the largest land animals ever to live, were still around in the southern hemisphere. Imagine a herd of Argentinosaurs, each weighing up to 80 or 90 tons. The sheer amount of vegetation they would consume, digest, and process would be staggering. And like modern ruminant herbivores, such as cows, their digestive processes would likely have produced vast quantities of methane, another powerful greenhouse gas. So in this alternate timeline, as the continents continue to drift and the climate naturally begins its long, slow, cooling trend towards the Cenozoic ice ages, you have a powerful biological force pushing in the other direction. The continued existence of these mega-herbivore dinosaurs, especially the sauropods, could have acted as a significant source of greenhouse gases. This might have buffered the planet against cooling. It could have delayed or even prevented the onset of the ice ages. The planet's thermostat would have been set a few degrees warmer, not by geology alone, but by the persistent metabolism of its dominant life forms. This is a system-level consequence. It's not about intention. The dinosaurs are not trying to warm the planet. They are simply living, eating, and digesting. But the collective effect of their existence, scaled up to a global level, becomes a planetary force. It's a beautiful example of how life doesn't just adapt to a passive planetary stage, it helps to build the stage itself. There is no top-down control, no design. It is an emergent property of a complex coupled system. What are the second-order effects of this planetary feedback model? If the survival of dinosaur mega-herbivores kept the planet warmer for longer, what else would change as a result? Let's follow the chain of if-then consequences. If the planet remains warmer, then the polar ice caps, which began to form in our timeline around 34 million years ago in Antarctica, might form much later, or not at all. Without large ice sheets locking up vast amounts of water, global sea levels would be significantly higher, coastlines would be in different places, large parts of what are now continents would be shallow epicontinental seas. This creates a different map of the world. More shallow seas mean more marine habitat, which could lead to a different evolutionary path for ocean life, but it also means less land area. The continents would be smaller islands, which could lead to greater isolation and the evolution of unique island fauna, much like we saw in Australia or Madagascar in our timeline. So, the continued existence of a sauropod on a continent in the southern hemisphere could, through a long and complex chain of causality involving methane, atmospheric chemistry, and global temperature, ultimately affect the evolution of a small predator on a completely different continent by changing the very shape of the land it lives on. Now let's consider the plants. A warmer, higher CO2 world is a very different environment for plant life. In our timeline, the cooling and drying of the Cenozoic, combined with lower CO2 levels, created the evolutionary pressure that led to the rise of grasslands. Grasses developed a new, more efficient type of photosynthesis called C4, which is well adapted to hot, dry, low CO2 conditions. But in a world that remains warmer, wetter, and richer in CO2, the advantage of C4 photosynthesis is greatly reduced. The old C3 photosynthesis used by most trees and shrubs works just fine. So, the great grass and grazer savanna ecosystems that cover so much of our modern world might never have evolved. The planet might have remained a world of forests, woodlands, and vast fern prairies. This would have a profound impact on animal evolution. Grazing is a very different lifestyle from browsing on leaves and shrubs. It requires different types of teeth, different digestive systems, and different body plans. The magnificent diversity of mammalian grazers in our world, horses, antelope, bison, camels, rhinoceroses, is a direct result of the spread of grasslands. In a world without widespread grasslands, dinosaurian herbivores would have continued to evolve as browsers, leading to different kinds of creatures. Perhaps we would see more high browsers like the sauropods and giraffes, or more selective, low browsers like hadrosaurs and deer. The very texture of the dominant ecosystems would be different. This demonstrates the sensitivity of the system, a subtle shift in the planet's energy budget maintained by the biological activity of one group of animals can prevent the emergence of an entire biome that, in our world, covers nearly a third of the land surface. The world we are building feels more and more different from our own, not just in its cast of characters, but in its very bones, its geography, its climate, and its botany. It shows that causality in Earth systems is not a straight line, but a web. Pull on one thread, the survival of the sauropods, and the entire web trembles, and its pattern rearranges in ways that are complex, far-reaching, and entirely unintentional. Wherever you are listening to this and at whatever time, take just a moment to check in with yourself. Perhaps you are in your bed, with the day fully behind you, or maybe you're in a comfortable chair, letting the evening wind down. Maybe it's the middle of the night, and you've woken seeking a calm voice to guide you back to rest. Just notice that. Acknowledge the specific time and place you inhabit. This journey into deep time, into a world so alien and distant, can feel untethering. But you are here now, grounded, The simple act of noticing your own presence is a powerful anchor. We are a community of curious minds scattered across the globe in countless different rooms and time zones, but united for this brief period by a shared sense of wonder. If this journey is providing you with a measure of peace or sparking a gentle curiosity, perhaps you might consider subscribing or leaving a quiet like. There is no pressure. Think of it as leaving a small, silent token of appreciation, a signal that this kind of slow, thoughtful exploration is something you value. It helps others who are also seeking a quiet space for their minds to find their way here. But the most important thing is that you feel comfortable, that you feel your mind beginning to soften and open. That is the only real goal. So let that thought go and let's return to our journey. Let the world outside your window, with its familiar sounds and lights, fade into the background once more. We are about to step back across that 66 million year divide, back into the world that continued. To be fair to our own timeline, we must give the mainstream explanation its due. Why do the vast majority of scientists believe that the non-avian dinosaurs did in fact go completely extinct? The case is overwhelmingly strong, built from multiple independent lines of evidence that all point to the same dramatic conclusion. Let's steelman that argument, presenting it in its most robust form. The story begins with a thin layer of clay. In the late 1970s, the geologist Walter Alvarez and his father, the Nobel Prize-winning physicist Luis Alvarez, were studying a rock formation in Gubbio, Italy. They were interested in a strange, thin layer of clay that marked the boundary between the Cretaceous period and the Tertiary period, now called the Paleogene. This is the KT boundary, or as it's now known, the KPG boundary. They wanted to know how long it took for that clay layer to be deposited. They decided to measure the concentration of the element iridium in the clay. Iridium is very rare on the Earth's surface, but it is much more common in meteorites and asteroids. The idea was that a slow, steady rain of cosmic dust would add a tiny, constant amount of iridium to the sediments. By measuring the total amount in the clay layer, they could calculate the time it represented. But when they got the results back, they were stunned. The iridium levels were not just slightly elevated, they were hundreds of times higher than in the rock layers above and below. It was a massive, global spike. This was too much to be explained by a slow rain of dust. The Alvarez team proposed a radical hypothesis that this iridium spike was the chemical fingerprint of a massive asteroid, some 6 to 10 miles wide, that had slammed into the Earth, vaporizing on impact and spreading a cloud of iridium-rich dust all around the globe. This was the smoking gun. But a hypothesis needs more than one piece of evidence. And in the years that followed, the evidence poured in. Scientists found the same iridium spike at the KPG boundary in dozens of locations worldwide in both marine and terrestrial rocks. It was a truly global signal. They also found other impact markers in the same layer. There were shocked quartz grains, crystals of quartz whose internal structure had been deformed by the immense pressure of an impact. There were tektites, small, glassy spheres of rock that had been melted in the blast and flung for thousands of miles. The evidence pointed to a single catastrophic event of unimaginable violence. But where was the crater? For a decade, the location of the impact remained a mystery. Then, in the early 1990s, geophysicists piecing together gravitational and magnetic anomaly maps of the Gulf of Mexico found what they were looking for. Buried under a half-mile of younger sediments centered near the town of Chicxulub on the Yucatan Peninsula was a massive impact crater over 100 miles in diameter. Its age? 66 million years. The pieces all fit. The impact would have been apocalyptic. The initial blast would have vaporized everything for hundreds of miles. It would have triggered earthquakes of a magnitude we can barely imagine and colossal tsunamis that would have scoured coastlines halfway around the world. But the real killer was what happened next. The immense heat from the impact and the re-entry of debris flung into space would have created a pulse of thermal radiation, broiling the surface of the Earth and igniting global wildfires. Then, the vast cloud of dust and soot from the impact and the fires would have enshrouded the planet in darkness for months, perhaps years. This was the impact winter. Photosynthesis would have shut down on land and in the oceans. The base of the food chain would have collapsed. Plants would have died. Herbivores would have starved, and then the carnivores that fed on them would have starved. The fossil record tells this story with brutal clarity. Below the KP boundary, you find a rich diversity of dinosaur fossils. Above it, they are gone, all of them. The only dinosaurs to survive were the birds, and it wasn't just the dinosaurs. The giant marine reptiles, the pterosaurs, the ammonites in the oceans, all vanished. It was a selective extinction. Small animals, animals that could burrow, animals that could eat decaying matter, like our small mammalian ancestors, had a better chance of surviving the initial devastation and the long winter that followed. The mainstream model is powerful because it explains all of this evidence: the global iridium layer, the shocked quartz, the tektites, the crater itself, and the specific pattern of extinction we see in the fossil record. It is a cohesive, evidence-based narrative of planetary catastrophe. While the impact hypothesis is the cornerstone of our understanding of the end Cretaceous extinction, it is important to present the full picture, which includes alternative interpretations and acknowledges the complexities that still exist. Science is rarely a closed book, and even in a case as strong as this, there are nuances and ongoing debates that enrich our understanding. One significant factor occurring at the same time as the impact was a period of immense volcanic activity in a region of India known as the Deccan Traps. Over a period of hundreds of thousands of years, straddling the KP boundary, a series of volcanic eruptions of almost unimaginable scale spewed out enough lava to cover an area half the size of India in a layer of basalt rock thousands of feet thick. This was not a normal volcanic eruption. It was a flood basalt event, one of the largest in Earth's history. Such massive volcanism would have had severe global consequences. It would have released vast quantities of sulfur dioxide, leading to acid rain and short-term cooling. More importantly, it would have pumped enormous amounts of carbon dioxide into the atmosphere, leading to long-term, intense global warming. For a long time, there was a debate in the scientific community: was it the asteroid or the volcanoes that killed the dinosaurs? Was Chicxulub the smoking gun, or just the final nail in the coffin? The modern consensus does not see these as mutually exclusive explanations. Instead, it's increasingly viewed as a 1-2 punch. The ecosystems of the late Cretaceous were likely already under severe stress from the climate change being driven by the Deccan Traps. The planet was swinging between periods of volcanic winter and intense greenhouse warming. Life was struggling. Then into this already stressed world came the asteroid, delivering a catastrophic blow that the weakened ecosystems simply could not recover from. This more nuanced model presents a world that was not a stable paradise suddenly shattered, but one that was already sick and then received a mortal wound. There are also alternative interpretations of the fossil record itself. Some paleontologists have argued that the diversity of dinosaurs was already in decline for several million years leading up to the KP boundary. They point to fossil formations in North America that seem to show fewer species present in the final stages of the Cretaceous. If this is true, it suggests that the dinosaurs were already on their way out, and the impact and volcanoes simply hurried along an inevitable process. However, this interpretation is highly contested. Other researchers argue that this apparent decline is an artifact of the fossil record, a phenomenon known as the Signor Lips effect, where the patchiness of fossil preservation can make a sudden extinction look like a gradual one. More recent and comprehensive studies of the global dinosaur fossil record suggest that they were, in fact, thriving and diverse right up until the very end. The debate highlights an important unknown. We don't have a perfect, continuous movie of the past. We have snapshots, fragments of a story, and how we interpret those fragments matters. So we have two major catastrophic events, an impact from above and a volcanic upheaval from below, happening at almost the same geological moment. It's a case of terrible, cosmic bad luck. Our thought experiment, what if the dinosaurs never went extinct, becomes more complex. To save them, do we just remove the asteroid, or do we need to quiet the Deccan traps as well? For the sake of our journey, we have adopted the simpler premise that the asteroid was the primary killer, and that without it, the dinosaurs, while stressed by the volcanism, would have ultimately adapted and survived as life has survived other massive volcanic events in Earth's history. But it is important to hold this complexity in mind. The world we are saving was already a world in turmoil. How do we know what we know about a world that is 66 million years old? Our knowledge is not direct. It is inferred, pieced together like a detective story, with most of the clues missing and the witnesses long dead. Understanding the limits of our methods is crucial for maintaining a sense of humility and realism in our imaginative journey. Our primary source of information is the fossil record, but the fossil record is notoriously, profoundly incomplete. The process of fossilization is incredibly rare. An animal has to die in the right place, be buried quickly by sediment before it is scavenged or decays, and the sediments have to turn to rock. Then those rocks have to survive millions of years of geological turmoil, uplift, erosion, metamorphosis, without being destroyed. And finally, they have to be exposed on the surface, in a place where a paleontologist can find them. The number of things that have to go right is immense. It has been estimated that we have found fossils for far less than 1% of all the species that have ever lived. So when we look at the fossil record, we are not looking at a complete encyclopedia of past life. We are looking at a few scattered, torn-out pages. This is the problem of survivorship bias. What we see is only what was lucky enough to be preserved. We have a much better record of large animals with sturdy bones that lived in lowland floodplains where burial is common than we do of small, delicate creatures that lived in upland forests, where erosion is the dominant force. This means our picture of the past is inherently skewed. There are entire ecosystems, entire branches of the tree of life that may be completely invisible to us. When we say that mammals in the Mesozoic were all small, shrew-like creatures, we are saying that based on the evidence we have, is it possible that there were larger, more diverse mammals that lived in environments where their fossils were unlikely to form? It's possible, though the consistent pattern of small size across many different fossil sites makes the standard interpretation very likely to be correct. Our instruments for seeing the past also have detection limits. We reconstruct ancient climates by analyzing the chemical isotopes in fossil shells or rocks. This gives us a good picture of average global temperatures over long periods. But it doesn't tell us what the weather was like on a Tuesday in the late Cretaceous. We see the broad strokes, the long-term trends, but the fine-grained, lived experience of these animals is lost to us. Our knowledge is like a low-resolution image. We can make out the major shapes and colors, but the fine details are blurred. This is not a reason for despair. It is a reason for intellectual caution. It means that when we build our alternate timeline, we are building it on a foundation that has gaps. We have to be comfortable with uncertainty. We have to be willing to say, we don't know, or this is one possibility, but there are others. This awareness of our own detection limits is what separates a disciplined thought experiment from pure fantasy. It keeps us tethered to the evidence, even as we explore what lies beyond its direct reach. So, as we reopen the main thread of our journey, let's carry this understanding with us. Our imagined world of surviving dinosaurs is built from the fragments that survived. It is a reconstruction, a plausible ghost, built around a skeleton of hard-won but incomplete scientific fact. The gaps are not a weakness in the story. They are an invitation for our curiosity to fill them in, gently and thoughtfully. The words we use to describe the past are not neutral containers of fact, they are frames, and the way we frame a story fundamentally shapes how we understand it. In paleontology and in our journey tonight, the language we choose is especially important because we are trying to describe systems and processes that are alien to our everyday human experience. One of the most common traps is the use of anthropomorphic language, attributing human intentions, emotions, or goals to non-human entities, especially to the process of evolution itself. We often hear phrases like, evolution's goal was to create more complex beings, or nature designed the tyrannosaur to be a perfect killer. This kind of language is a useful shorthand, but it is deeply misleading. Evolution has no goals, nature has no intentions. These are mindless, undirected processes. A tyrannosaur is not a design. It is the current endpoint of a long line of ancestors, each of whom happen to have traits that allowed them to survive and reproduce in their specific environment. The perfection we see is an illusion, a retrospective story we tell ourselves. The animal was simply good enough to get by. So in our exploration, we will try to be precise with our language. Instead of saying nature designed a feature, we might say a feature was selected for because it conferred a survival advantage. Instead of talking about evolution trying to solve a problem, we will talk about how a changing environment created a selective pressure that favored certain traits over others. This may seem like a small change, but it has a profound effect on our perspective. It removes the sense of an overseeing intelligence and replaces it with the much more mysterious and awe-inspiring reality of emergent complexity. Similarly, we must be careful with our metaphors. We have already used the metaphor of the arms race to describe coevolution. It's a powerful image, but it has limits. A real arms race involves conscious actors, nations with strategies and goals. The evolutionary version is a blind, reactive process. The prey does not decide to evolve a defense against the predator. A random mutation might occur that happens to make an individual slightly more defended. That individual is more likely to survive and pass on that mutation. Over generations, the trait spreads. There is no strategy, only differential survival. We will continue to use metaphors because they are essential for understanding complex ideas. We will talk about feedback loops, thermostats, and archives in the rock, but we will hold them lightly. We will remember that they are tools to help our human minds grasp a non-human reality, not literal descriptions of that reality. The map is not the territory. By being mindful of our language, by replacing words of intent with words of process, and by clarifying the limits of our metaphors, we can approach this lost world with a greater sense of clarity and respect. We can see it not as a failed prequel to our own story, but as a completely different story with its own logic, its own rhythm, and its own unique forms of being. This careful use of language helps to maintain the calm, observational, and non-judgmental tone that is so important for our journey tonight. It keeps our curiosity pure, free from the distortions of human-centered narratives. Let's now try to apply some of these ideas in a more concrete way. Imagine yourself not as a disembodied observer, but as a time traveler, standing on a single spot of Earth, watching the world change around you over millions of years. Let's use the template of the coevolutionary arms race, the pattern we see at the human scale, and walk through a plausible chain of cause and effect in our alternate timeline. Let's place you in what will one day be the Great Plains of North America, around 50 million years ago, which is 16 million years after the asteroid failed to strike. In our timeline, this was a world of strange, early mammals. But in this world, the dinosaurs still rule. The climate has cooled somewhat from the Cretaceous hothouse, and the dense forests are beginning to thin in places, creating a patchwork of woodland and open fern prairie. You are watching a herd of herbivores. They are descendants of the duck-billed hadrosaurs, but they have changed. The selective pressure from predators in this more open landscape has made them faster. Their legs are longer and more slender, their bodies leaner. They are no longer just browsers of leafy vegetation. Their beaks have become broader and tougher, adapted to cropping the tough ferns and cycads that dominate these clearings. They have also evolved more sophisticated social behaviors. They move in a large, coordinated herd. Sentinels stand at the edges, their crests, now larger and more complexly shaped, held high, scanning the horizon. They communicate with a series of low, resonant calls, amplified by the hollow chambers in their crests. Now, a predator appears at the edge of the clearing. It is a descendant of the dromaeosaurs, the raptors, but it too has changed. It is larger than its Cretaceous ancestors, perhaps the size of a grizzly bear. It is still feathered, but its body is built for pursuit in the open. It is a cursorial predator. It cannot take on a healthy adult hadrosaur alone. The arms race has seen to that, so it does not hunt alone. You see two others emerge from the woodland, moving with a terrifying, coordinated grace. They are pack hunters. The lead raptor makes a feint, driving the herd into a panicked run. The other two sprint alongside, their sickle claws held off the ground, their eyes fixed on a single target, a younger, less experienced hadrosaur at the edge of the group. They use flanking maneuvers, trying to separate it from the safety of the herd. The hadrosaurs respond not with chaos, but with a practiced defensive strategy. The larger adults maneuver themselves between the predators and the vulnerable young, forming a moving wall of flesh, their powerful tails ready to lash out. The low, booming calls coordinate their movements. This is the arms race in action. The predators evolved pack hunting to overcome the defenses of the herd. The herd, in response, evolved more complex communication and cooperative defense to counter the pack. Every day is a test. Every hunt is a new move in a chess game played out over millions of years. And you, the observer, can see the next step. You can see the selective pressure that this interaction is creating. The raptors that are smarter, better at communicating and coordinating are the ones that will eat. The hadrosaurs that are better at reading the predator's intent, better at communicating warnings, are the ones that will survive. This single, recurring interaction, happening thousands of times a day across the continent, is a relentless engine for increasing intelligence and social complexity in both lineages. You are witnessing in this vivid, concrete example the raw material for the evolution of a different kind of mind. It's not a guarantee, but a powerful potential, born from the simple, brutal logic of survival. Now let's shift our scale. Let's pull back from that single, dramatic scene of the hunt and look at the same world through the lens of systems and feedback loops. We will apply the logic of our second evidence track to this same time and place 50 million years ago in our dinosaur-dominated North America. How does the macro-scale perspective change what we see? The scene we just witnessed, the raptor pack and the hadrosaur herd, is not happening in a vacuum. It is one small component of a vast, interconnected biomechanical system. Let's consider the soil beneath their feet. In our timeline, the evolution of grasses and grazing mammals created the deep, rich prairie soils of the American Midwest. The grasses have dense, fibrous root systems that hold the soil together, and the cycle of growth and decay, aided by the digestive systems of bison and other grazers, builds up a thick layer of organic matter. But in this world, there are no grasses and no bison. The dominant plants are ferns and cycads, and the dominant herbivores are dinosaurs. How does this change the system? Dinosaurs have a different kind of metabolism from mammals. As reptiles, even warm-blooded ones, their metabolic rate may have been lower. Their digestive systems were different, likely less efficient at breaking down tough plant matter. The result is that the nutrient cycling in this ecosystem would be slower. The waste produced by a herd of hadrosaurs would be different chemically from that produced by a herd of bison. This would lead to a different community of insects and microbes in the soil responsible for decomposition. Over millions of years, these small differences in chemistry and process add up. The soil of this fern prairie might be thinner, less rich in certain nutrients, and perhaps more prone to erosion. The landscape itself is being shaped by the biology of its inhabitants. Now let's consider the atmosphere. A single large hadrosaur might weigh 10 tons. A herd of 500 of them is a 5,000-ton river of biomass moving across the landscape. The amount of carbon dioxide they release with every breath is significant. The amount of methane their digestive systems might produce is also a factor. Scale this up across the entire continent, across all the different dinosaur species, and you have a biological input into the global carbon cycle that is completely different from the mammalian system of our world. As we discussed earlier, this could contribute to a warmer global climate. Let's quantify this slightly. Climate models suggest that the complete removal of all large methane-producing herbivores today would have a measurable cooling effect on the planet. It is plausible, then, that a world full of dinosaurian megafauna would maintain a baseline global temperature that is a few degrees warmer than a world of mammalian megafauna, all other things being equal. This seemingly small difference of a few degrees has enormous consequences. It changes rainfall patterns. It affects ocean currents. It determines which plants can grow where. The actions of the raptors and hadrosaurs in our small scene are constrained by these macro-level conditions. The very existence of the open fern prairie where they hunt is a result of these global temperature and CO2 levels, so the micro-scale drama of the hunt and the macro-scale stability of the planetary climate are not separate stories. They are the same story, told at different scales. The hunting strategies of the raptors are shaped by the landscape, and the landscape is shaped by the collective metabolism of all the dinosaurs on the planet. This is the essence of a complex system. Everything is connected. The breath of a single dinosaur, multiplied by billions and sustained over millions of years, helps to compose the world that its distant descendants will inherit. Let's zoom out even further now, beyond the biosphere, beyond the climate, to a scale of celestial mechanics. The Earth is not alone in space. It is locked in an intimate dance with its companion, the Moon. This relationship, the planet-moon coupling, is not a static backdrop. It is a dynamic system that has profound and evolving consequences for the habitability of our planet. The most obvious effect of the Moon is the tides. The Moon's gravitational pull creates a bulge in the Earth's oceans, and as the Earth rotates, this bulge sweeps across the planet as the high tide. But the Earth rotates faster than the Moon orbit. This means the tidal bulge is always slightly ahead of the Moon in its orbit. The Moon's gravity then pulls back on this bulge, acting like a brake on the Earth's rotation. This process is called tidal friction. It is a slow, relentless transfer of angular momentum from the Earth's spin to the Moon's orbit. The consequences of this are twofold. First, the Earth's rotation is slowing down. The day is getting longer. When the dinosaurs lived, a day was not 24 hours long. It was closer to 23 and a half. 400 million years ago in the Devonian period, a day was only 22 hours long. If we go back far enough to the early days of the Earth-Moon system, a day may have been as short as 5 or 6 hours. This rotational damping is a fundamental process of planetary evolution. Second, as the Earth loses rotational energy, that energy is transferred to the Moon, which pushes it into a higher orbit. The Moon is slowly drifting away from the Earth at a rate of about 1.5 inches or nearly 4 centimeters per year. In the time of the dinosaurs, the Moon was closer. It would have appeared larger in the sky, and the tides would have been stronger. Now, why does this matter for life on Earth? The Moon's presence has a crucial stabilizing effect. The Earth is tilted on its axis by about 23.5 degrees relative to its orbit around the Sun. This tilt is what gives us our seasons. But this tilt is not inherently stable. The gravitational pulls of the Sun and other planets, especially Jupiter, would cause the Earth's axial tilt, or obliquity, to wobble chaotically over long periods. Our tilt could swing wildly from 0 degrees, no seasons, to as much as 85 degrees, extreme seasons, with the poles pointing almost directly at the Sun. A planet with such unstable seasons would be a very difficult place for complex life to evolve and thrive. The Moon, our large, close companion, acts as a gyroscope. Its gravitational influence dampens these chaotic wobbles and keeps the Earth's axial tilt stable within a narrow range. This has given our planet a stable, predictable climate over geological timescales, which has been incredibly important for the evolution of life. In our alternate timeline, this process continues just as it did in ours. The day continues to lengthen, the Moon continues to drift away. Over 66 million years, the day would have lengthened by about another half hour, and the Moon would have moved about 1,600 miles further away. This is a slow background rhythm of planetary change that is independent of biology. It is a reminder that our world is not just shaped by life and geology, but also by its place in the solar system. The deep, slow tick of the celestial clock governs the fundamental parameters of the world in which our surviving dinosaurs must live and evolve. The consequences of this slow, celestial dance are profound, translating the cold physics of tidal friction into the lived reality of geological time. The gradual slowing of the Earth's rotation and the Moon's steady retreat are not just astronomical trivia. They have direct impacts on planetary habitability and the course of evolution. Let's consider the lengthening of the day. A day that was 23.5 hours long at the end of the Cretaceous would become, in our alternate present, roughly 24 hours long, just as it is for us. This seems like a small change, but over millions of years it alters fundamental climatic patterns. The rotational speed of a planet is a key factor in its weather. A faster spinning planet tends to have more but smaller weather systems and stronger, more defined atmospheric bands like the jet streams. As the planet slows down, these weather systems can become larger, more energetic, and longer lasting. Think of Jupiter, which rotates in under 10 hours. Its atmosphere is dominated by incredibly stable, long-lived storms like the Great Red Spot. While the Earth's slowdown is much less dramatic, the principle holds. The weather patterns in the world of our surviving dinosaurs would have slowly, imperceptibly shifted over the eons. The average duration and intensity of storms might have increased. The boundaries between climate zones might have become less sharply defined. These are subtle but powerful selective pressures. For a flying creature, a shift in prevailing wind patterns could open up new migratory routes or close old ones. For a large land animal, an increase in the intensity of seasonal monsoons could change its entire habitat. Now let's think about the stabilizing effect of the Moon on the Earth's tilt. This stability is the gift that keeps on giving. By preventing our planet's axis from wobbling chaotically, the Moon ensures a certain predictability in the seasons over deep time. This doesn't mean the climate is static. Ice ages can still come and go due to other orbital cycles, known as Milankovitch cycles. But the fundamental pattern of winter, spring, summer, and fall remains a reliable rhythm. This long-term climatic stability is a crucial precondition for the evolution of complex, long-lived organisms and intricate ecosystems. It allows for the development of long-term evolutionary strategies like migration, hibernation, and the coevolution of plants and their pollinators. In a world with a chaotic, unpredictable axial tilt, life might be constantly knocked back to square one, unable to build up the kind of ecological complexity we see on Earth. So the continued presence of the Moon, acting as our planet's faithful gyroscope, is a non-negotiable part of our alternate world. It is a quiet, constant force that allows the drama of evolution to play out on a stable stage. The slow retreat of the Moon would have slightly weakened this stabilizing effect over the 66 million years, and the tides would have become less powerful, changing the dynamics of coastal ecosystems. But the fundamental gift of seasonal stability would have remained. When we imagine the life of a dinosaur in this alternate world, we must remember that its world was governed by these celestial rhythms just as much as ours is. The length of its day, the strength of the tides, and the predictable march of the seasons were all written by the silent, gravitational conversation between the Earth and the Moon. Let's return to the ground beneath our feet. We spoke earlier of the Earth's crust as an archive, a library of stone. How is this archive written, and what does its structure tell us about the limits of our knowledge? Now let's use a more detailed metaphor. Imagine the history of the Earth as a vast, continuous film. The fossil record is not a copy of that film. Instead, imagine that every few thousand years a single, random frame is saved. Most of the film is lost forever. Then those few saved frames are buried, crumpled, torn, and water-damaged. Many are completely destroyed. What paleontologists do is to find these surviving damaged frames and try to piece them together in the right order to understand the story. This is the nature of our archival evidence. Sedimentary rocks, the kind that preserve fossils, are laid down in layers or strata. The principle of superposition is simple. In an undisturbed sequence of rocks, the oldest layers are at the bottom and the youngest are at the top. This gives us a relative timeline. We can say that a triceratops is older than a woolly mammoth because its fossils are always found in deeper, older layers of rock. To get absolute dates, we use radiometric dating. Certain elements, like uranium, have unstable isotopes that decay into other elements, like lead, at a known constant rate. By measuring the ratio of the parent isotope to the daughter isotope in crystals within volcanic ash layers, we can calculate how long ago that ash was deposited. If we find a fossil just below a layer of ash dated to 66.5 million years ago, and just above another layer dated to 67 million years ago, we know our dinosaur lived sometime in that half-million-year window. This method is incredibly powerful, but it has its limitations. It only works for igneous rocks like volcanic ash, not the sedimentary rocks where fossils are usually found. So we are often dating the layers above and below the fossil, not the fossil itself. This gives us a date range, not a precise moment. The archive is also geographically biased. We have incredibly rich fossil records from certain parts of the world, like the American West, where the geology and climate are perfect for preserving and exposing rocks of the right age. But there are other places, like tropical rainforests, where rocks are deeply buried and chemical weathering is intense, from which we have almost no fossil record at all. We know dinosaurs must have lived in the Amazon basin, for example, but we have very few fossils to tell us what they were like. Our archival signal is strong in some places and completely silent in others. This patchiness means that global events can be hard to interpret. Was the apparent decline in dinosaur diversity before the impact a real biological event, or does it just reflect the fact that most of our best late Cretaceous fossils come from one small part of North America? It's like trying to understand global human history by only looking at the historical records of a single town in Italy. You'll get a very detailed but very localized picture. The archive itself, the way the story is recorded, imposes constraints on the kinds of questions we can answer. We are very good at tracking the broad evolutionary history of lineages over millions of years. We are much less good at understanding the population dynamics of a single species from year to year. We see the lagging indicators, the final results of processes that took place over immense stretches of time. The lived moment-to-moment reality is almost entirely lost. This is the beautiful and frustrating nature of deep time archives. They give us a breathtaking view of the grand sweep of history, but they deny us the intimacy of the present moment. What are the implications of these archival constraints for our thought experiment? How does the fragmented, biased nature of the fossil record shape what we can and cannot confidently infer about our alternate world? Firstly, it forces us to be humble about the level of detail we can plausibly create. While we can sketch out the broad evolutionary trends, tyrannosaurs might get faster or smaller, hadrosaurs might evolve more complex social structures. We cannot know the specific forms they would have taken. We can't know for sure what color feathers an advanced dromaeosaur would have had, or the exact notes of a new hadrosaur's call. To claim such specific knowledge would be to mistake our disciplined imagination for a direct vision of the past. So we must speak in terms of archetypes and possibilities. We can talk about the evolution of a large cursorial pack-hunting dromaeosaur as a plausible occupant of a new ecological niche without having to name the species or draw its exact anatomy. This maintains a respectful distance, acknowledging that the real world in all its contingent detail would have been far richer and stranger than we can imagine. Secondly, the patchiness of the archive means that major events could have happened in our alternate timeline that we would have no way of predicting. In our own Cenozoic history, there were moments of abrupt climate change, like the Paleocene-Eocene thermal maximum, a rapid global warming event that had a major impact on evolution. There were also contingent events like the formation of the Isthmus of Panama, which connected North and South America and led to a massive interchange of animal species. Our alternate world would have had its own unique contingent events and surprising turns. Perhaps a new disease evolves and wipes out a dominant group of herbivores, opening up niches for another. Perhaps a new mountain range rises, creating a rain shadow and turning a lush forest into a desert, driving a burst of evolutionary innovation. We cannot predict these things. We can only assume that the history of this world would have been just as complex and unpredictable as our own. The story would not be a simple, linear extrapolation of Cretaceous trends. It would be a messy, chaotic, and beautiful history, full of twists and turns. Our confidence bands, therefore, must be very wide. We can be fairly confident that mammals would have remained small and marginalized. We can be fairly confident that dinosaurs would have continued to diversify and adapt to the changing geology and climate. But as we get more specific, our confidence must decrease. The idea of a sapient dinosauroid evolving is a fascinating possibility, but it is at the very edge of our plausibility spectrum. It is not a prediction, it is an exploration of a remote possibility. By acknowledging what the archival signals can and cannot tell us, we can navigate our thought experiment with more intellectual honesty. We are not discovering a lost history, we are constructing a plausible one. And the most plausible history is one that acknowledges its own immense, unknowable gaps. It is in those gaps, in that uncertainty, that the true sense of wonder can be found. As our picture of this alternate world begins to take shape, built from these different tracks of evidence and inference, we can start to see a larger synthesis emerging. We have looked at the small scale of coevolution, the planetary scale of climate feedbacks, and the celestial scale of the Earth-Moon system. We have also considered the very nature of our knowledge, the dusty, fragmented archive from which we draw our clues. Soon we will begin to weave these threads together more tightly. We will try to build a more holistic portrait of this world, to see how these different scales of process interact and influence one another. How does the slow lengthening of the day, driven by the moon, affect the hunting strategies of a pack of predators evolving over millions of years? How does the chemical composition of the atmosphere, influenced by the metabolism of dinosaur herds, shape the very rocks that will one day form the fossil archive? These are the kinds of questions that a systems-level view allows us to ask. We are moving from looking at the individual pieces to understanding how the machine works as a whole. But before we get there, we need to add a few more crucial pieces to our model. We need to look more closely at the conversation between the living world and the atmosphere, and at the very code of life itself. So let's hold this thought, this promise of a coming synthesis, as a gentle guidepost for the next stage of our journey. We are gathering the threads, and soon we will begin to see the pattern they create. Let's dive deeper into one of the most beautiful and complex feedback loops on our planet, the conversation between the biome and the atmosphere. This is not a one-way street where life simply endures the weather. Ecosystems actively participate in creating their own climate, particularly when it comes to the water cycle. Consider a vast forest, like the Amazon rainforest. It is often called the lungs of the planet, which is true in that it exchanges vast quantities of carbon dioxide and oxygen. but it is also a giant heart pumping water into the atmosphere. A single large tree can pull hundreds of gallons of water from the soil through its roots and release it into the air as vapor through tiny pores in its leaves, a process called transpiration. Scaled up to the size of a whole forest, this is a colossal amount of water vapor. This moisture doesn't just disappear, it rises, cools, and condenses to form clouds. In this way, the forest generates its own rain. Studies have shown that a significant portion of the rainfall in the interior of the Amazon is recycled water, moisture that has been transpired by the forest itself. The forest creates the very conditions it needs to survive. This is a powerful, stabilizing feedback loop. But the conversation is even more sophisticated than that. Plants and the fungi and bacteria that live on them release tiny particles into the atmosphere called aerosols. These can be pollen, fungal spores, or complex volatile organic compounds, the chemicals that give a forest its distinctive smell. These aerosols act as cloud condensation nuclei. Water vapor in the atmosphere needs a surface to condense onto to form a cloud droplet. Without these particles, clouds would have a much harder time forming. So, the forest is not just providing the moisture for rain, it is also providing the seeds around which raindrops can form. It is an active, participating agent in weather creation. Again, we must depersonify this. The forest does not want to make rain. It is an emergent property of millions of individual organisms, each pursuing their own survival. The trees that are better at managing their water supply and contributing to a stable local climate are the ones that are more likely to thrive and reproduce. Over evolutionary time, this leads to an ecosystem that becomes incredibly effective at regulating its own environment. Now let's transport this mechanism to our alternate world. Imagine the vast, warm, inland plains of North America 60 million years ago. In our version of events, without the rise of grasses, these might be dominated by immense fern prairies. Do ferns transpire and release aerosols in the same way that a tropical rainforest does? Yes, but the structure is different. A fern prairie has a much lower leaf area index than a multi-layered forest canopy. It is a two-dimensional surface rather than a three-dimensional volume, so it would be less efficient at recycling water. This ecosystem might be more prone to drought and fire. However, the dinosaurs themselves would be part of the loop. A giant herd of hadrosaurs moving through this prairie would be a major source of aerosols, dust kicked up by their feet, skin particles, spores from their dung. They would be walking cloud seeders. Their presence could, unintentionally, increase the probability of rainfall in their own habitat. We see a similar phenomenon today, where large herds of mammals on the African savanna can influence local weather patterns. Here we have another beautiful, complex feedback, a three-way conversation between the plants, the animals, and the atmosphere. The health of the fern prairie depends on the rain depends on the clouds depend on the aerosols, and the aerosols are provided by both the ferns and the dinosaurs. It is a self-sustaining system, a web of unintentional collaboration that creates a stable world for its inhabitants. Every system has its limits. Feedback loops can maintain stability, but they can also break down. Understanding the resilience, the thresholds, and the failure modes of these systems is crucial for painting a realistic picture of our alternate world. Let's stay with our example of the fern prairie and its self-generated rainfall. This system works well as long as the components remain within a certain range. But what happens if an external force pushes the system too hard? Imagine a long-term cyclical drought driven by slow changes in ocean currents that lasts for several centuries. The rainfall decreases. The ferns, which are not as deeply rooted or as drought-resistant as many modern grassland plants, begin to die back. As the plant cover thins, the rate of transpiration drops. Less water vapor is pumped into the atmosphere. This, in turn, further suppresses rainfall, which causes more ferns to die. This is a positive feedback loop. A change in one direction triggers a response that amplifies that same change. The system has crossed a threshold and is now tipping into a new, alternative stable state. The fern prairie collapses and is replaced by a much drier scrubland, or even a desert. The dinosaurs that depended on the prairie would be in crisis. The large herds of hadrosaurs would have to migrate or face starvation. The predators that hunted them would have to follow. The entire ecosystem would undergo a dramatic reorganization. This is the logic of tipping points. A system can appear stable and resilient for a long time, absorbing minor shocks and disturbances. But there is a point beyond which it cannot recover, and it rapidly transitions into a new state. Our alternate world, just like our own, would have been subject to these dynamics. Its history would not have been one of smooth, gradual change. It would have been punctuated by these abrupt shifts as ecosystems crossed critical thresholds and reconfigured themselves. Fire is another key factor. In a seasonally dry fern prairie, fire could be a major driver of change. A lightning strike could ignite a blaze that sweeps across hundreds of square miles. But fire is not just a destructive force, it's a creative one. Some ecosystems, like the chaparral in California or the savannas of Africa, are fire-adapted. The plants have evolved strategies to survive or even thrive on regular fires. It's possible that over millions of years these fern prairies would have co-evolved with fire. Perhaps some ferns would develop fire-resistant rhizomes underground, allowing them to resprout quickly after a burn. The fires would clear out dead material and return nutrients to the soil. For the dinosaurs, fire would be a terrifying and powerful force. It would reshape their landscape, drive their migrations, and create both peril and opportunity. Some animals might learn to follow the fires, feeding on the roasted remains of smaller creatures. The system develops a new kind of resilience, one that incorporates fire as a regular part of its cycle. This introduces a certain liveliness or unpredictability into our world. It is not a machine that runs smoothly. It is a dynamic, chaotic system that is constantly being tested. Its stability is not guaranteed. Its history is written in these moments of collapse and renewal. The failure of one feedback loop can be the birth of a new kind of ecosystem. Resilience is not about staying the same forever. It's about the capacity to absorb change and reorganize, to persist in a new form. This more dynamic view makes our alternate world feel more real, more alive, and more subject to the same kinds of dramatic transformations that have shaped the history of our own Earth. Let's now turn our attention from the grand scale of ecosystems to the microscopic world of genetics. We can think of the DNA of an organism as a kind of biological code, an operating system that has been written and rewritten over billions of years of evolution. This analogy is powerful, but like all analogies, it requires careful caveats. DNA is not a blueprint, carefully designed by an engineer. It is more like a vast, ancient and messy codebase, full of legacy code, redundant subroutines, and commented-out sections, what we call junk DNA. It is a program that was not designed but rather evolved through a process of random mutation and natural selection. There is no programmer. The environment is the tester, and survival is the only metric of success. The code that works, that produces an organism capable of reproducing in its environment, is passed on. The code that fails is deleted. When we talk about 66 million more years of dinosaur evolution, we are talking about another 66 million years of this code being edited, debugged, and expanded. The fundamental operating system of life, the basic chemistry of DNA, RNA, and proteins, would remain the same. But the specific applications, the genes that code for things like feather color, bone density, or digestive enzymes, would be constantly changing. Let's consider the concept of Hox genes. These are a group of master control genes that lay out the basic body plan of an animal during embryonic development. They determine where the head goes, where the limbs sprout, and how many vertebrae are in the spine. They are the high-level architectural code. A small mutation in a Hox gene can have a dramatic effect, like causing a leg to grow where an antenna should be in a fruit fly. This ancient, highly conserved toolkit of genes would be the raw material for dinosaur evolution. Evolution is often a tinkerer, not a grand inventor. It rarely creates entirely new features from scratch. Instead, it repurposes existing structures controlled by this ancient genetic code. A ceratopsian's horn is not a new invention, it is a modification of the bone and skin that make up the skull. The wings of a pterosaur, a bird, and a bat are all modifications of the same basic vertebrate forelimb. The genetic code for build a limb was simply tweaked and redeployed to create these different structures. So, as we imagine our future dinosaurs, we should think of them as variations on existing themes. The genetic operating system they inherited from their Cretaceous ancestors would constrain the kinds of evolutionary paths available to them. You wouldn't suddenly see a dinosaur evolve 6 legs because the underlying Hox gene code for vertebrates is strongly wired for 4 limbs. But you could see incredible modifications of those 4 limbs. You could see the arms of a tyrannosaur descendant become longer and more robust, re-evolving into functional grasping appendages. You could see the hind legs of a hadrosaur become even more specialized for running. You could see the elaborate frills and crests of ornithischian dinosaurs evolve into even more spectacular and diverse forms driven by sexual selection. The genetic code provides both the potential for change and the constraints that channel that change in certain directions. It is the raw material, the programming language in which the story of evolution is written. And 66 million years is a very, very long time for that code to be edited. It's enough time for small, incremental changes to accumulate into transformations that would make these creatures seem like entirely new beings, yet they would still carry the deep, ancient syntax of their dinosaurian ancestors in every cell of their bodies. The biology as code analogy helps us frame evolution, but its most important implication is what it tells us about resilience and the nature of good design in a biological system. In human engineering, we often strive for perfection and efficiency. We want our code to be clean, elegant, and optimized to perform a single task perfectly. A failure is a bug that needs to be fixed, but biological systems are not designed this way. They are messy, redundant, and often inefficient. And this messiness is the very source of their incredible robustness and resilience. Think about the genetic code itself. There is a lot of redundancy built into it. There are often multiple genes that can perform similar functions. If one gets a harmful mutation and stops working, another can often take up the slack. This is like having backup systems in a critical piece of machinery. The system is not perfectly efficient, but it is much less likely to have a catastrophic failure. Biological systems are designed to fail gracefully. Our imagined future dinosaurs would embody this principle. They would not be perfect killing machines or perfect eating machines. They would be collections of good enough solutions that had been cobbled together over eons. Their bodies would be full of evolutionary baggage, structures and genes that were holdovers from a previous way of life. For example, some snakes still have the tiny vestigial remnants of hind legs buried in their muscles, a genetic echo of their 4-legged lizard ancestors. A future tyrannosaur might still have the genetic code for 3 fingers on its hand, even if it only expressed 2, just like the T-Rex did. This imperfection is not a flaw. It is a feature. The messiness of the genetic code, the presence of this junk DNA and these vestigial genes, provides a reservoir of genetic diversity. It is a library of old ideas that can be reactivated or repurposed if the environment changes. A gene that was once used for producing a certain kind of feather pigment might, with a small mutation, be co-opted for a role in the immune system. A suppressed developmental pathway could be reactivated, leading to the re-emergence of a lost trait, a phenomenon known as an atavism. This makes the system incredibly adaptive. It can dip back into its own evolutionary history to find solutions for present-day problems. The system prioritizes robustness over perfection. It doesn't seek a single, optimal solution. It maintains a whole portfolio of possibilities. When we think about the survival of the dinosaurs in our alternate world, this is the key. They would face immense challenges, changing climates, new diseases, shifting continents. They would survive not because they were perfectly adapted to any one condition, but because their messy, redundant, and historically deep genetic code gave them the flexibility to adapt to many different conditions. They would be resilient. Their systems would fail gracefully. An individual might die, a species might go extinct, but the larger lineage would have the inherent capacity to change and persist. It is a different kind of engineering, one that values redundancy, flexibility, and a deep respect for the lessons of the past. It's a philosophy of survival that is written into the very code of life itself. Let's now travel back even further in time to build an unfamiliar world that existed long before even the dinosaurs we know. This is a crucial piece of context because the world of the dinosaurs was itself a product of an even deeper history, a history of planetary configurations so alien they challenge our imagination. Let's journey back to the Permian period, roughly 250 million years ago. At this time, almost all of the Earth's landmass was fused together into a single, colossal supercontinent. We call it Pangea. Picture it in your mind. No Atlantic Ocean. North America is pressed hard against Europe and Africa. South America is tucked into Africa's western coast. India, Australia, and Antarctica are fused together on the southern end. It is a single, immense world continent, surrounded by a single, immense world ocean, Panthalassa. Now let's build the sensory experience of this world. The climate of a supercontinent is a climate of extremes. The sheer size of the landmass prevents moisture from the ocean from penetrating deep into the interior. So while the coastal regions might be lush and monsoonal, the vast heartland of Pangea would have been an immense, arid desert, larger than any desert on Earth today. Imagine standing in this desert. The sun is harsh and white in a pale, dusty sky. The heat is oppressive, the air is thin and dry. The landscape is a vast, monotonous expanse of red rock and sand, stretching to a shimmering horizon. There are no flowering plants yet, no grasses. The vegetation, where it exists, is tough and hardy. Seed ferns, cycads, and hardy conifers clinging to life in dry riverbeds. The animals that live here are not dinosaurs. They are our own distant relatives, the synapsids, often called mammal-like reptiles, as well as strange amphibians and early reptiles. You might see a herd of moschops, stocky, hippo-sized herbivores with thick skulls, moving slowly through the heat. You might see the formidable predator Dimetrodon, famous for the large reptilian sail on its back, which it probably used to regulate its body temperature. This is a world that feels ancient, stark, and deeply alien. Now let's imagine the end of this world. The Permian period did not end quietly. It ended in the most catastrophic mass extinction event in Earth's history, the Great Dying. An immense volcanic event in Siberia, even larger than the Deccan Traps, pumped the atmosphere full of greenhouse gases, triggering runaway global warming and ocean anoxia. Over 90% of marine species and 70% of terrestrial species were wiped out. It was the closest life has ever come to being completely extinguished. Pangea was sterilized. It was from the ashes of this catastrophe on this single, giant continent that the dinosaurs first evolved. They arose in the aftermath, in the Triassic period, from a small group of reptilian survivors. Their success was, in part, a story of being in the right place at the right time, filling the ecological void left by the Great Dying. This deep time context is essential. The dinosaurs were children of Pangea. Their early evolution and spread across the globe was only possible because all the land was connected. An early dinosaur could, in theory, walk from the future site of New York City to the future site of Beijing. It was this initial global distribution that set the stage for their long reign as Pangea began to break apart in the Jurassic and Cretaceous, carrying the different dinosaur lineages with it on the newly forming continents, where they would then evolve in isolation. The existence of a supercontinent like Pangea has profound consequences for the planet's climate and the biomes that can exist upon it. These consequences are not just historical, they reveal fundamental principles of how planets work. The primary driver of a supercontinent's climate is a concept called continentality. Land heats up and cools down much faster than water. A large body of water, like an ocean, acts as a huge thermal buffer, moderating the climate of nearby land. Coastal regions have milder seasons, with cooler summers and warmer winters than inland regions. When you have a continent as vast as Pangea, this effect is magnified to an extreme. The interior of the continent is thousands of miles from the moderating influence of the ocean. This creates a brutal climate. The summers would be incredibly hot, with temperatures far exceeding anything we experience today. The winters, without the stored heat of the ocean to warm the air, would be bitterly cold. The diurnal temperature swing, the difference between day and night, would also be extreme. The defining feature of the Pangean interior would be its aridity. The prevailing winds would pick up moisture from the Panthalassan Ocean, but they would drop it all as rain on the coastal regions. By the time the air masses reached the interior, they would be bone dry. This creates a vast rain shadow over the heart of the continent. This is why the interior of Pangea was a massive desert. This geography severely limits the kinds of life that can exist. Only the most drought-resistant and temperature-tolerant organisms could survive in the interior. Life would be concentrated along the coasts and in the few large river systems that might have managed to penetrate the arid core. This has huge implications for biodiversity. Instead of a world with many different isolated continents, each with its own unique fauna and flora, you have one giant landmass. This can lead to lower global biodiversity as the same few hardy species become widespread, and there are fewer opportunities for isolated populations to evolve into new species. The breakup of Pangea was a major driver of biodiversity in Earth's history. As the continents rifted apart, they created new coastlines, new shallow seas, and new milder climates. They isolated populations of animals and plants, setting them on their own unique evolutionary paths. This is why the dinosaurs of the late Cretaceous in North America were so different from those in South America or Asia. They had been evolving in isolation for tens of millions of years. For our alternate timeline, this deep history matters. The dinosaurs who survived the non-extinction event were the heirs of this great continental breakup. Their world was one of increasing isolation and provincialism. If we were to run the clock forward, this trend would continue. The continued northward drift of Africa and India, crashing into Europe and Asia, would create new mountain ranges like the Alps and the Himalayas. These mountains would create new rain shadows and new climate patterns, driving further evolutionary change. The world of our 66-million-year-old dinosaurs would be a world shaped by the slow, relentless fragmentation of the ancient supercontinent that gave them their start. Even the most robust and widely accepted scientific theories must be constantly tested and questioned. That is the nature of the scientific process. So let's step into the shoes of a committed skeptic for a moment. What are the strongest criticisms one could level against our entire thought experiment? What are the potential falsifiers, the pieces of evidence that could prove our imagined world to be impossible? The first and most powerful criticism would be aimed at the premise of dinosaur survival itself. A skeptic would argue that the dinosaurs were already a group in decline, an evolutionary dead end, and that the asteroid was merely the coup de grace. The evidence for this, as we've noted, is contested, but a skeptic would emphasize it. They might point to the apparent lack of dinosaur diversity in the latest Cretaceous rocks and argue that the mammals, with their higher metabolism, intelligence, and reproductive strategies, were already beginning to outcompete them. In this view, even without the asteroid, the dinosaurs would have slowly faded away during the Cenozoic, eventually being replaced by the more advanced mammals. Our world of thriving, evolving dinosaurs would be a biological impossibility. A second line of attack would focus on the climate. The Cenozoic era, in our timeline, was characterized by a long, steady cooling trend, culminating in the Pleistocene ice ages. A skeptic would argue that the dinosaurs, as primarily large-bodied ectothermic or mesothermic reptiles, were poorly adapted for a colder world. They were creatures of the Mesozoic greenhouse. As temperatures dropped, they would have struggled to maintain their body temperatures and find enough food. The ice ages, with vast continental glaciers covering much of North America and Eurasia, would have been the final blow. Only small, burrowing, warm-blooded and intelligent mammals could have survived such conditions. Our vision of dinosaurs adapting to this new world is, in this view, wishful thinking. A potential falsifier for our premise would be the discovery of clear, unambiguous evidence that the majority of dinosaur groups were in a steep, global decline for millions of years before the impact. If new fossil sites around the world consistently showed a crash in dinosaur diversity while mammal diversity was exploding, it would seriously weaken the idea that they could have persisted. Similarly, if detailed physiological models based on dinosaur bone histology proved conclusively that they could not have regulated their body temperature in a cooling world, our scenario would be in trouble. Another major criticism could be leveled at the idea of intelligent dinosaurs. A skeptic would argue that intelligence of the humankind is a bizarre evolutionary fluke, not a predictable trend. They would point out that for 150 million years, dinosaurs showed no trend towards the kind of tool use, language, or abstract thought that characterizes humans. Why would another 66 million years be any different? The largest brains in the dinosaur world belonged to small predators, but even these were not exceptional compared to modern birds or mammals. The idea of a dinosauroid civilization, the skeptic would say, is pure science fiction, an anthropocentric projection of our own qualities onto creatures that were fundamentally different. To counter this, one would need to concede that this is indeed the most speculative part of the thought experiment. We must acknowledge that human-like intelligence is not an inevitable outcome of evolution. However, we can also point to the clear trend of increasing brain size, encephalization, in both mammals and birds during the Cenozoic. It seems to be a general adaptive response to the complex challenges of a changing world. It is plausible, though not certain, that at least some dinosaur lineages would have followed a similar path. By honestly presenting these strong criticisms and acknowledging where our speculation is on thin ice, we make our inquiry stronger, not weaker. It shows that we are engaged in a good faith exploration of possibilities, not a dogmatic defense of a single outcome. Let's pause for a moment and reflect on the process we are engaged in. Our journey is an exercise in a particular kind of thinking, a detective mindset applied to a crime with no witnesses, the crime of an erased history. We are sifting through incomplete layers of evidence, trying to reconstruct what was lost. At the heart of this process is the concept of a prior. A prior is the initial belief or assumption we bring to a problem before we've seen the evidence. In our case, our prior is that the world of the late Cretaceous was a functioning, resilient ecosystem, and that its inhabitants were not destined for extinction. We started with the assumption that they would have survived without the asteroid. We then look for evidence that either supports or challenges that prior. The fossil record, the climate data, the principles of evolutionary biology, these are the clues we examine. But we must also be aware of the problem of anomalies. An anomaly is a piece of data that doesn't fit the prevailing theory. The iridium spike was a classic anomaly. Before the Alvarezes, the prevailing theory for the extinction was a gradual decline driven by climate change and volcanism. The iridium spike was a sharp, strange signal that didn't fit. A good detective or a good scientist pays close attention to anomalies. They are the cracks in the old story that can let the light of a new understanding in. In our alternate world, we must imagine that its history would also be full of anomalies that its future paleontologists, whoever they might be, would puzzle over. Perhaps they would find a strange, thin layer of soot in the rocks from 66 million years ago, a hint of the massive wildfires from the Deccan traps, and debate for centuries what could have caused it. Then there is the profound problem of erasure. History is not just written, it is also erased. The geological processes of erosion and subduction are constantly destroying the archives of the past. The further back we go in time, the less rock is available for us to study. The story gets fainter, the pages more tattered. We are working with a palimpsest, a manuscript that has been written on, scraped clean, and written on again. The faint traces of older stories are all that remain. This meta method, this awareness of how we are thinking, is a vital part of the journey. It prevents us from falling into the trap of certainty. It reminds us that we are building a model, a simulation, and that the simulation is not the real thing. It is a tool for thought. And by understanding the tool, we can better understand the meaning of what it produces. So let's reopen our main thread, but with this detective's mindset renewed. We are holding our priors lightly. We are watching for anomalies, and we are deeply, humbly aware of the vastness of what has been erased. The silence that surrounds the few, faint signals we can still detect. This is the space in which our careful curiosity can thrive. Let's bring our awareness back from the vastness of deep time to the immediate human scale of your own body in this room. The journey we are on can be abstract, full of immense timescales and complex systems. It's important to keep reconnecting it to a felt, embodied reality. So once again, notice your breath, the simple, rhythmic, unconscious process of air moving in and out of your lungs. This process, respiration, is your personal connection to the planet's great energy budget. You are taking in oxygen, a byproduct of billions of years of photosynthesis, a gift from ancient bacteria and plants. You are using it to metabolize the energy stored in the food you've eaten, energy that ultimately came from the sun. And you are exhaling carbon dioxide, the very same greenhouse gas that we've been discussing on a planetary scale. You are a tiny, walking, breathing component of the Earth's carbon cycle. Your body is a microcosm of the planetary systems we have been exploring. You have feedback loops that regulate your temperature, your blood sugar, your hydration. You have an archival code in your DNA that carries the history of your ancestors. You are a complex, adaptive system, and you have agency. Not the kind of agency to change the planet's orbit, but the agency to change your own state. You can choose to take a slightly deeper breath. You can choose to shift your position to be more comfortable. You can choose to let go of a thought that is causing you tension. This is not a prescription or an instruction. It is simply an observation, an invitation to notice the connection between the grand, impersonal systems of the planet and the intimate, personal system that is you. By feeling these processes in your own body, the abstract concepts of feedback, regulation, and energy flow become more tangible, more real. The story of the planet is not a story that is happening out there. It is also happening in here. You are made of the same stardust, governed by the same physical laws and participating in the same great cycles of matter and energy as the dinosaurs we have been imagining. This human-scale reset is not a departure from our topic. It is the very heart of it. It is about understanding that we are not separate from the natural world, but an expression of it. And by grounding our grand intellectual explorations in this simple, felt reality, we keep the journey from becoming unmoored. We keep it human. We keep it meaningful. Now, with that renewed sense of embodied connection, let's apply this way of thinking to our world of dinosaurs. Let's look at the planet through the lens of energy budgets and flows. This is a powerful, quantitative way to understand why a world is the way it is. The ultimate source of energy for almost all life on Earth is the sun. Plants capture a tiny fraction of this solar energy through photosynthesis and store it in chemical bonds. This is the primary production of the planet, the foundation of the entire food web. All the energy that herbivores get from eating plants and all the energy that carnivores get from eating herbivores is just this captured solar energy being passed along a chain. But at each step, a huge amount of energy is lost, mostly as heat. This is a fundamental law of thermodynamics. It means that the total biomass of plants in an ecosystem must be much, much larger than the total biomass of herbivores, and the total biomass of herbivores must be much, much larger than the total biomass of carnivores. This creates an energy pyramid. The wide base is the plants, the next level up is the herbivores, and the tiny peak is the top predators. This simple concept of an energy budget imposes powerful constraints on what is possible in an ecosystem. Let's think about a T-Rex. A single adult T-Rex weighed around 8 or 9 tons. To fuel a body that large, especially if it was warm-blooded and active, would have required a colossal amount of energy. It would have needed to eat a huge number of herbivores. This means that the ecosystem it lived in must have been incredibly productive. The base of the energy pyramid, the plant life, must have been growing at a fantastic rate to support the massive herds of hadrosaurs and ceratopsians that the T-Rex preyed upon. The high CO2 levels and warm, wet climate of the late Cretaceous created just such a world of explosive plant growth. Now let's run this forward into our alternate Cenozoic. As the climate cools and CO2 levels drop, the overall primary productivity of the planet might decrease. The base of the energy pyramid shrinks. This has inevitable consequences for the levels above it. There is simply less energy available to support giant animals. This would create a strong selective pressure for dinosaurs to become smaller. The era of the true giants, like the 80-ton sauropods or the 9-ton tyrannosaurs, might have come to an end, not because of a sudden catastrophe, but because the planet's energy budget could no longer support them. So, the descendants of T-Rex 66 million years later might be much smaller animals. Perhaps the largest land predator on Earth in this alternate present would be a 1-ton tyrannosaurid, still a formidable beast, but a shadow of its ancestor. The herbivore herds would also likely be smaller, both in individual body size and in total numbers. The entire metabolism of the biosphere would have had to slow down to adjust to a planet with a tighter energy budget. This is not a story of failure or decline, it is a story of adaptation. The dinosaurs would be responding to the fundamental physical and chemical constraints of their changing world. By thinking in terms of these energy flows, we can make more disciplined predictions. We can see how a change in a single parameter, atmospheric CO2 concentration, can ripple up through the entire food web, reshaping the bodies and the lives of the creatures within it. It replaces vague speculation with a more rigorous cause and effect logic. The consequences of this energy budget model lead to a series of fascinating second-order trade-offs and a richer understanding of the system's sensitivity. We've established that a cooling, low CO2 world would likely favor smaller dinosaurs. But what other evolutionary pathways does this open up? Let's conduct a brief sensitivity analysis. Let's assume the cooling trend is not uniform. Some parts of the world, like the equatorial regions, might remain relatively warm and productive. These areas could act as refugia for the true megafauna. Perhaps the last of the giant sauropods would be found only in the Amazon basin of this alternate world, while smaller, more derived forms populated the rest of the globe. This creates a world with more geographical diversity, a mosaic of ancient holdovers and new evolutionary innovations. Now consider the trade-offs of body size. Being large has advantages. You are safer from predators, you are more thermally stable, you lose heat more slowly, and you can eat a wider range of lower quality food. But being large also has huge disadvantages. You need a massive amount of food, you reproduce very slowly, and your populations are therefore smaller and more vulnerable to sudden environmental changes. Being small, on the other hand, means you need less food, you can reproduce much more quickly, and your populations can be larger and more resilient. But you are more vulnerable to predation and to fluctuations in temperature. The shifting energy budget of the planet would change the calculus of this trade-off. As the climate became less stable and food resources less abundant, the advantages of being small would start to outweigh the advantages of being large for many lineages. This is likely why mammals, in our timeline, remained small for so long and then radiated into large forms only when the climate was stable and productive. So, in our dinosaur world, we might see an age of small dinosaurs. Perhaps the most diverse and successful groups would not be the descendants of T-Rex and Triceratops, but the descendants of the smaller, more adaptable dinosaurs like the ornithomimids, the ostrich mimics, or the pachycephalosaurs, the dome-headed dinosaurs. These smaller, faster, and possibly more intelligent creatures would have been better equipped to deal with a more dynamic and less bountiful world. This leads to a multiplicity of plausible mechanisms. There isn't one single, correct future for the dinosaurs. There is a whole fan of possibilities. Some lineages might have gone the route of size reduction. Others might have adapted by evolving more efficient metabolisms, getting more energy out of less food. Still others might have developed new behaviors like long-distance migration to follow the seasonal availability of resources. And of course, many lineages would have simply gone extinct, unable to adapt to the new conditions. This is the nature of evolution. It is not a single path, but a delta of branching streams. Our uncertainty budget here is quite large. We cannot know which of these strategies would have been the most successful. But by understanding the fundamental constraints of the energy budget and the trade-offs involved, we can map out the space of plausible outcomes. The world we are building becomes less of a single, fixed image and more of a dynamic landscape of competing evolutionary strategies, all shaped by the slow, relentless arithmetic of energy flow. How have humans throughout history made sense of deep time and the existence of strange, giant beings from a lost world? Long before the science of paleontology, people were finding dinosaur fossils. These enormous bones eroding out of hillsides and riverbanks must have been a source of immense wonder and fear. Lacking a scientific framework for understanding extinction and evolution, they interpreted these remains through the lens of their own cultures and stories. They mapped these unfamiliar patterns onto their existing narratives. In many parts of the world, these giant bones were seen as the remains of dragons. The griffin, a mythical creature with the body of a lion and the head and wings of an eagle, is a classic example. The historian Adrienne Mayer has compellingly argued that the myth of the griffin originated with nomadic Scythian gold miners in Central Asia, who encountered the fossil skeletons of the horned dinosaur Protoceratops eroding out of the Gobi Desert. The skeleton of a Protoceratops with its 4 legs, its beaked face, and its bony neck frill that could easily be mistaken for wings is a remarkably close match for the description of a griffin. The miners would have seen these skeletons guarding the desert, the same areas where they were searching for gold. And so a story was born, the griffin, a fierce creature that guards hidden treasures. This is a beautiful example of a pre-scientific culture making a direct, empirical observation of the fossil record and integrating it into their worldview through the power of myth. In China, dragon bones have been used in traditional medicine for centuries. Many of these bones are, in fact, the fossilized remains of dinosaurs. The dragon is a powerful and auspicious symbol in Chinese culture, a composite creature associated with water, weather, and imperial power. The discovery of these giant reptilian bones would have naturally reinforced and enriched the existing dragon myths. In Native American traditions, the discovery of giant bones was often interpreted as the remains of the thunderbirds, powerful beings who created storms, or of great monsters who were slain by cultural heroes in a mythical age. These stories serve to explain the inexplicable and to place these strange findings within a meaningful cosmic order. What these cultural lenses show us is a deep human need to make sense of the world, to weave observations into a coherent narrative. The patterns were there in the rock, waiting to be seen. The way they were interpreted depended on the operating system of the culture that found them. The myths of dragons, griffins, and giant thunder beasts were not just fantasies. They were the first human attempts to grapple with the reality of a deep past, populated by incredible and unfamiliar creatures. They were a form of proto-paleontology, an expression of the same human curiosity that drives our scientific inquiry today. Our journey tonight is, in a way, a continuation of this ancient tradition. We are using a different toolkit, the toolkit of science, but the fundamental impulse is the same, to look at the fragments of a lost world and to wonder, what story do they have to tell us? We have now assembled a number of different threads, different ways of looking at our alternate world. We have the thread of co-evolutionary arms races, driving sophistication at the local scale. We have the thread of planetary feedback loops, where life shapes its own environment. We have the thread of celestial mechanics, the slow rhythm of the moon's retreat. We have the thread of the messy, resilient genetic code. And we have the thread of the planetary energy budget, which places hard constraints on what is possible. All these threads have been telling a similar story, a story of adaptation, complexity, and interconnectedness. Now we are approaching a point where we can begin to weave them together. We are ready for a turn, a reframing of our initial question. We started by asking, what if dinosaurs never went extinct? As if it were a simple binary, an on or off switch. But our exploration has shown us that the world is not made of simple binaries. It is a world of continua, of shades of grey. The next stage of our journey will be to move beyond the simple what if and to ask a more nuanced question. How would the continued presence of the dinosaurs change the very nature of the planetary system? How would this alternate Cenozoic era differ from our own, not just in its inhabitants, but in its fundamental dynamics, its rhythm of change, its capacity for resilience? This is the synthesis we have been building towards. The real turn in our thinking comes when we move beyond seeing the survival of the dinosaurs as a simple substitution, swapping out mammals for reptiles, and start to see it as a fundamental change in the operating system of the Cenozoic biosphere. We are moving from a binary choice, dinosaurs or mammals, to a continuum of possibilities, a different planetary state. In our timeline, the Cenozoic has been the age of mammals, but it has also been, more fundamentally, the age of endothermy. Endotherms, or warm-blooded animals like mammals and birds, generate their own internal heat. This allows them to be active in a wide range of temperatures, but it comes at a tremendous energetic cost. An endotherm needs to eat 10 times as much food as an ectotherm, a cold-blooded animal, of the same size just to stay alive. Our world is a high-energy biosphere. The dominant animals run hot, live fast, and burn through a huge amount of the planet's primary production just on maintenance. Now consider the world of the dinosaurs. The debate about their metabolism is complex, but many were likely mesotherms, somewhere in between true cold-blooded ectotherms and hot-blooded endotherms. They generated some internal heat, but their large body size also helped them maintain a stable temperature through sheer thermal inertia. The key point is that their overall metabolic rate, their energy throughput, was likely lower than that of a comparable mammal. A dinosaur-dominated Cenozoic would therefore be a lower energy biosphere. The pace of life might be literally slower. The rate at which nutrients are cycled through the ecosystem, from plant to herbivore to carnivore and back to the soil, would be slower. Think about the lived choice, the daily reality for these creatures. A lion in our world might need to make a kill every few days to fuel its high metabolism. A large theropod predator of the same size in the alternate world might only need to eat once a week or once a fortnight. Its whole life would be structured around a different rhythm of energy expenditure and consumption. This seemingly subtle difference in metabolic rate, when scaled up to the entire planet, would have profound consequences. It would change the carrying capacity of ecosystems. It might affect the global cycles of carbon and nitrogen. It could even change the long-term evolutionary dynamics. A lower energy system might be more stable, less prone to the rapid booms and busts we see in some mammal populations. But it might also be slower to recover from disturbances like climate shifts or disease outbreaks. This reframing moves us away from simply populating our world with fantastic creatures and towards thinking about the deep structural properties of the system itself. We are no longer just asking who lives in this world, but how does this world live? What is its pulse, its rhythm, its fundamental metabolic signature? This is a much deeper and more interesting question. It suggests that the absence of the Chicxulub impact didn't just save the dinosaurs, it preserved a whole different mode of being for the terrestrial biosphere, a different solution to the problem of how to organize life on a planetary scale. The world we are exploring is not just our world with lizards instead of lions. It is a fundamentally different kind of planet. Let's now attempt a first synthesis, weaving together our different evidence tracks into a minimal, coherent model of this alternate world. We will try to connect the micro to the macro, building a picture of how the different scales of process would interact. Our starting point is the late Cretaceous world, with its high CO2 levels, warm climate, and incredible productivity. We remove the asteroid, and we allow the Deccan Traps volcanism to play out. This causes a period of climatic instability and some extinctions, but the dinosaurs as a whole pull through. They enter the Paleocene epoch, a world still reeling from the volcanism, but fundamentally theirs. The first major consequence, as we've established, is the continued suppression of the mammals. They remain small, nocturnal, and occupy the margins. This is our foundational assumption. The second consequence is that the dinosaurs themselves must now adapt to the long-term Cenozoic cooling trend, which is driven by geological factors like continental drift and mountain building. This is the primary selective pressure for the next 66 million years. This is where our energy budget track comes in. The cooling climate and dropping CO2 levels reduce the planet's primary productivity. The energy pyramid shrinks. This places a strong constraint on body size. So our first major prediction is a general trend towards smaller dinosaurs. The age of the true giants is over. This is not a failure but a successful adaptation to a less bountiful world. Now let's bring in the co-evolution track. As the landscape changes, with forests giving way to more open woodlands and fern prairies, new kinds of predator-prey dynamics emerge. On the open plains, speed and intelligence become more important than brute strength. This drives the arms race between new, leaner tyrannosaurid or dromaeosaurid predators and their hadrosaurid or ceratopsian prey. This is the engine of behavioral and cognitive evolution. The pressure is on to become smarter, faster, and more social. This is where we see the potential, though not the certainty, for the evolution of higher intelligence in some lineages. Now let's overlay our biome-atmosphere feedback track. The nature of these new ecosystems, dominated by ferns instead of grasses and dinosaurian herbivores instead of mammals, creates a different set of climate feedbacks. The water cycle is different. The methane cycle is different. The planet's thermostat is set slightly differently. Perhaps this dinosaurian biosphere has a slight warming effect, which would buffer the planet against the most extreme cooling of the ice ages. The glaciers might still advance, but perhaps not as far. This would mean that more of the northern continents would remain habitable for dinosaurs throughout the glacial cycles. Finally, all of this is happening against the slow, steady backdrop of our celestial track. The day is slowly getting longer, the moon is drifting away, and the seasons remain stable. This provides the reliable, long-term environmental canvas upon which these other, more dynamic changes are painted. Here is our integrated model, a world whose life is adapting to a long-term cooling trend constrained by a shrinking energy budget driven by co-evolutionary pressures towards greater intelligence, and all the while actively co-creating its own climate on a stable, predictable planetary platform. It is a world of smaller, faster, smarter dinosaurs living in ecosystems unknown to us, under a sky that is subtly different. This synthesis avoids triumphalism. It doesn't claim to know the exact outcome. Instead, it sketches the major forces, the constraints, and the likely directions of change. It provides a plausible, interconnected framework for our continued exploration. A good synthesis must not only integrate the evidence, but also honestly confront the counterpoints and the remaining uncertainties. Our model is plausible, but it is not the only possibility. Let's reconcile it with the criticisms we raised earlier and be explicit about what we still don't know. Our first major counterpoint was the idea that dinosaurs were already in decline and that mammals would have eventually outcompeted them anyway. Our model implicitly rejects this by assuming the dinosaurs were resilient enough to survive the Cenozoic challenges. How do we justify this? We can point to the 150 million years of dinosaur success, which suggests they were not a fragile group. We can also argue that the superiority of mammals is not a given. Dinosaurs had their own set of advantages, such as more efficient water conservation and a lower metabolic cost, which might have served them well in a changing world. However, we must concede a large area of uncertainty here. The outcome of a long-term competitive interaction between two major groups of animals is incredibly difficult to predict. It's possible the skeptic is right, and our dinosaur world would have slowly, continent by continent, given way to a mammalian one. Our model represents one of two equally plausible macroevolutionary scenarios. The second major objection was that dinosaurs, as reptiles, could not have survived the cold of the Cenozoic, especially the Ice Ages. Our model counters this by suggesting, first, that many dinosaurs were not simple cold-blooded reptiles, but had more advanced mesothermic metabolisms. Second, we point to the fossil evidence of dinosaurs living in the polar regions of the Cretaceous, showing they were already adapted to cold and darkness. Third, we hypothesize that the dinosaurian biosphere itself might have kept the planet warmer, mitigating the worst of the cold. However, the uncertainty here is also significant. We don't know the precise metabolic rates of most dinosaurs. We don't know their exact tolerance for cold. A major prolonged ice age could certainly have been a catastrophic extinction event for many dinosaur lineages. So what are the next tests? What would we need to find to increase our confidence in our model? A key piece of evidence would be more detailed physiological studies of dinosaurs. New techniques for analyzing bone microstructure and chemical isotopes are giving us better and better insights into their growth rates and metabolic activity. If these studies consistently show that a wide range of dinosaurs had high mammal-like or bird-like metabolic rates, it would greatly strengthen the case for their ability to survive a colder climate. Another crucial area of research is climate modeling. We could run sophisticated computer simulations of the Cenozoic climate, but with one key input changed: the presence of a dinosaur-dominated biosphere with its associated methane and CO2 production. If these models showed that this biological factor was sufficient to prevent the formation of massive ice sheets, it would be powerful support for our hypothesis. We must also name what remains fundamentally unknown. The evolution of intelligence is the biggest black box. While we can argue that the pressures for it existed, the actual emergence of abstract thought, language, and technology is such a complex and contingent event that it will always remain in the realm of deep speculation. We also cannot know the role that pure chance would have played. A different configuration of continents, a different volcanic eruption, a different disease, any of these could have sent the world down a completely different path. Our synthesis, then, is not a final answer. It is a working hypothesis, a plausible story that fits the available evidence, but one that is bounded by large regions of uncertainty and that is open to revision as new evidence comes to light. This is the honest and humble position we must take. Let's now walk through a vivid, concrete application of this synthesized model. Imagine yourself standing on the shores of a vast, shallow sea covering what will one day be Central Europe. The time is the late Oligocene, about 25 million years ago, which is 41 million years into our alternate timeline. The world is cooler than the Cretaceous, but still warmer than our present. In our timeline, this was the era of giant, hornless rhinos and strange, predatory mammals. But here, the scene is different. The forest behind you is not a broadleaf, deciduous forest. It is a mix of conifers and strange, advanced cycads. The air feels humid. You see movement on the shoreline. A family group of small dinosaurs emerges from the trees. They are ornithopods, distant descendants of animals like Hypsilophodon. They are about the size of deer, bipedal, and incredibly fast. Their skin is covered in a downy, insulating coat of proto-feathers, an adaptation to the cooler climate, a direct consequence of the planet's changing energy budget. They move cautiously, their large eyes scanning the surroundings. They are here to feed on the seaweed-like vegetation growing in the intertidal zone. This is a new behavior, an adaptation to a niche that, in our world, is filled by marine iguanas or wading birds. Their very existence is a product of the synthesis. They are small-bodied, energy budget, feathered for insulation, climate change, and exploiting a new food source, evolutionary pressure. Suddenly the family group gives a series of high-pitched, chirping calls and scatters. A new creature has appeared, trotting along the beach. It is a predator, a descendant of the tyrannosaur line, but it is not a giant. It stands about as tall as a man and is built like a greyhound, long-legged, slender, and clearly designed for speed. This is the product of the co-evolutionary arms race in this particular environment. To catch the fast ornithopods, it had to sacrifice size for agility. It moves with an intelligent, searching gaze. Its eyes are large and forward-facing. You are seeing the result of 40 million years of selective pressure for better sensory processing and hunting strategy. It ignores the small ornithopods and instead stares out at the shallow sea. It wades into the water, its movements slow and deliberate. It is hunting for fish or small marine reptiles. This is another surprise. This lineage of tyrannosaurs has adapted to a semi-aquatic lifestyle, much like the grizzly bears of our world that feast on salmon. It is a niche that was available, and evolution found a way to fill it. The scene before you is a perfect snapshot of our synthesized model. You see creatures whose bodies and behaviors have been shaped by the slow cooling of the planet, by the relentless pressure of the predator-prey arms race, and by the opportunities presented by new environments. And in the background, the very length of the day and the rhythm of the tides, governed by the moon, are slightly different from those of their Cretaceous ancestors, having subtly shaped the coastal environment where this drama unfolds. Everything is connected, from the global climate to the anatomy of a single claw, from the orbit of the moon to the hunting strategy of a single predator. Our exploration of this alternate world is not just an intellectual exercise. It can also be a source of practical insight, a way of training our attention and recognizing our own agency in the complex systems we inhabit. We cannot, of course, test the hypothesis of dinosaur survival, but we can practice the kind of thinking that our journey has cultivated. Let's translate the grand themes of our documentary into small, testable practices for your own life. One such practice is scale shifting. Throughout our journey, we have zoomed in and out from the micro scale of a single gene to the macro scale of a supercontinent. You can practice this in your daily life. Take a simple object in your room, perhaps a wooden table. Start at the human scale. You see its color, its texture, its function. Now, zoom in. Imagine the wood grain, the cellular structure of the tree it came from. Imagine the process of photosynthesis that built those cells, a tiny miracle of converting sunlight into matter. Now, zoom out. Think about the forest where that tree grew. Think about the ecosystem of that forest, the soil, the rainfall, the other creatures that lived there. Zoom out further. Think about the climate of the region that allowed that type of forest to grow. Think about the geological history of the land itself. By practicing this intentional shifting of scales, you start to see the deep, hidden interconnectedness of things. The ordinary table becomes a portal to a whole universe of stories. It is no longer just a thing, it is a nexus of relationships. Another practice is noticing feedback loops. Our world is full of them. Think about the simple act of making a cup of tea. You want the water to be hot, but not boiling over. You listen to the sound of the kettle. As it gets hotter, the sound changes. You are using auditory feedback to regulate the system. This is a negative feedback loop. Now think about a social interaction. You say something kind to a friend. They smile and respond warmly. This makes you feel good, so you are more likely to be kind in the future. This is a positive feedback loop. Start to look for these loops in your own life, in your relationships, in your habits, in your community. By seeing the world through the lens of feedback, you move from seeing a series of disconnected events to seeing a dynamic, interconnected system. This does not require moralizing or judgment. It is simply a way of seeing more clearly how things work. It can give you a greater sense of agency because you start to see where the leverage points are, where a small, mindful action can create a ripple of change through the system. These practices are a way of taking the insights from our journey into deep time and applying them to the here and now. They are a way of cultivating a systems thinking mindset, a way of seeing the world that is more holistic, more connected, and ultimately more full of wonder. What does the future hold for this alternate Earth? If we let our simulation run forward from our present day, what are the plausible scenarios and open questions that lie ahead? This is speculation layered upon speculation, so we must label our confidence levels clearly. One plausible long-term scenario is that the planet will continue its cooling trend, eventually descending into a full-blown ice age, perhaps more severe than the one in our own recent past. How would our dinosaurian world cope? This is a major open question. We have hypothesized that some dinosaurs would be well adapted to the cold, with insulating feathers and advanced metabolisms, but a world where vast ice sheets cover much of the northern continents would be an immense evolutionary challenge. We might see the evolution of truly polar dinosaurs, perhaps descendants of the tyrannosaurs or dromaeosaurs that become white-feathered apex predators of the ice, hunting the large, insulated herbivores that graze on the frozen tundra. Our confidence in this is low, but it is a plausible extension of the trends we've seen. Another major question is the fate of intelligence. We have established that the conditions for the evolution of higher intelligence exist in this world, but would it ever lead to technology? Let's imagine that one lineage, perhaps a descendant of the clever troodontids, crosses that threshold. They evolve true language, abstract thought, and the ability to manipulate their environment with tools. What would a non-human, non-mammalian, technological civilization look like? Their sensory world would be different. Their evolutionary history would be different. Their psychology might be utterly alien to us. Perhaps their technology would be more biological, based on genetic engineering rather than mechanical devices. This is at the very lowest end of our confidence scale. It is a thought experiment within a thought experiment. It is more science fiction than predictive science, but it is a fascinating avenue to explore. What about the mammals? Would they remain in the shadows forever? Perhaps not. In 66 million years, they too have been evolving. They have become incredibly successful in their small-bodied niches. It is possible that in some future crisis, a mass extinction event caused by a new volcanic eruption or a climate shift, the dinosaurs might finally falter, and the mammals, after an almost 200 million year wait, might finally get their chance to inherit the Earth. The future of this world, like our own, is not predetermined. It is a branching path, full of possibilities. The key takeaway is that evolution would not stop. The world would continue to be a place of dynamic change and endless creativity. The open questions are vast. We cannot know the answers, but the act of asking them, of imagining the possibilities, is what gives this journey its richness and its purpose. It reminds us that the story of life is never truly over. It is always unfolding, always becoming something new. We have spent this time together on a long and winding intellectual journey. We have built a world from first principles, debated its plausibility, and walked through its imaginary landscapes. But what does it all mean? How do we translate this complex model into a felt sense of meaning? Let's try to reframe the emotional core of our story. At the beginning, the idea of a world without humans might feel like a loss. Our own story, the one we place at the center of the universe, has been erased. There is a sense of absence, of elegy. But as we have explored this alternate world, a different feeling may have begun to emerge. We have replaced the story of our own triumphant arrival with a story of continuity, a story of a different kind of success, a different kind of beauty. We have seen a world that is not lesser for our absence. It is whole and complete on its own terms. The emotional journey is from a feeling of loss to a feeling of humility. It is the realization that our existence is a profound and beautiful accident, not a destiny. And in that humility there is a strange kind of liberation. It frees us from the burden of being the sole purpose of creation. We are not the point of the story. We are just one incredible chapter in a much, much larger book. There is also a shift from a sense of loneliness to a sense of connection. By understanding the deep, impersonal systems that govern a planet, the cycles of carbon and water, the dance of evolution, the flow of energy, we start to see that we are part of that same system. The feeling of being a separate, isolated observer begins to dissolve. We are not looking at nature from the outside, we are nature looking at itself. The breath in your lungs, the beat of your heart, the thoughts in your mind, these are not separate from the world. They are expressions of it. They are the universe experiencing itself in a particular human way. The final emotional reframe is from a sense of fragility to a sense of resiliency. We live in a time of anxiety about the future of our own world. We see systems that feel like they are on the brink of failure. But our journey into deep time shows us that the story of life on Earth is a story of incredible resilience. It is a story of catastrophe and recovery, of endings and new beginnings. Life, as a planetary phenomenon, is tough. It has survived impacts, volcanoes, and ice ages. It adapts, it changes, it persists. This does not absolve us of our own responsibilities, but it can provide a sense of perspective, a deep time context for our present struggles. It can replace a feeling of frantic anxiety with a calmer, more grounded sense of purpose. We are part of a very old, very resilient story. Where does our scientific inquiry end, and where does the search for meaning begin? This is a philosophical boundary that our journey has brought us right up against. It is important to know where to draw the line. Our model of the alternate Cenozoic is built on data, on the principles of physics, biology, and geology. We can talk about the plausible metabolic rates of dinosaurs, the chemical composition of the atmosphere, the biomechanics of their movement. These are questions that have answers, even if those answers are difficult to find and are wrapped in uncertainty. We can make testable predictions, we can debate the evidence. This is the realm of science. But when we ask, what is the purpose of it all? Or is a world with intelligent dinosaurs better or worse than a world with humans? We have crossed a boundary. We have left the world of data and entered the world of values. Science can tell us how a star burns, but it cannot tell us why we find a starry night beautiful. It can describe the evolutionary process that led to the human mind, but it cannot tell us how we ought to use that mind. There is no experiment we can run that will tell us whether a world without us would be more or less meaningful. The question itself assumes a framework of meaning that science is not equipped to provide. So we must hold these questions open. We must allow them to be questions without demanding a final verdict from our scientific model. Our documentary can provide the raw material for this philosophical reflection. It can give us a new perspective, a new context for our own lives. It can provoke us to think about our place in the cosmos, about the nature of intelligence, about the meaning of existence. But it cannot give us the answers. The answers to these questions are not found in the fossil record. They are found in the human heart, in our art, in our philosophy, in our spiritual traditions, and in the quiet conversations we have with ourselves in the dead of night. Our journey has been an exercise in building a plausible is. We have tried to describe a world that might have been. The task of deriving an ought, of deciding what this story means for how we should live, is a separate and deeply personal one. By respecting this boundary, we honor both the power of the scientific method to illuminate the world and the power of the human spirit to find meaning within it. We can hold the awe and the data in our hands at the same time. As we approach the end of our journey, we are left with a fundamental question about how we interpret the world we have built and the real world we inhabit. Are we looking at a system that was designed or a system that simply emerged? These two frames, one of anthropic or design-based thinking and the other of emergent properties, can seem to be in conflict, but they can also be held in parallel as two different languages for describing the same sense of awe. The design frame is intuitive to us. We are tool makers. We see the world and we see what appears to be incredible design. The eye is like a camera. The wing of a bird is like an airfoil. The genetic code is like a computer program. It is natural to look at the intricate perfection of a living thing and feel that it must have been designed by a creator, an intelligence. From this perspective, the universe seems fine-tuned for our existence. The physical constants are just right. The Earth is in the perfect spot in the solar system. The asteroid struck at just the right time to clear the way for us. It all seems to be part of a plan, a story written for us. The emergence frame offers a different perspective. It says that there is no designer, no plan. Instead, complexity arises spontaneously from the interaction of simple components following simple rules. A flock of birds creates its beautiful, coordinated patterns not because a leader is directing them, but because each individual bird is following a few simple rules. Stay close to your neighbors, match their speed, and don't collide. From these simple local rules, a complex global order emerges. From this perspective, the universe is not fine-tuned for us. We are fine-tuned to the universe. We evolved to fit the conditions that exist. Life is not a miracle that violates the laws of physics. It is a natural, perhaps even inevitable, outcome of the laws of physics playing out on a planetary scale over billions of years. Our dinosaur world fits perfectly into this emergence frame. It is a world of unintended consequences, of feedback loops, of complex systems arising from the simple drive of organisms to survive and reproduce. There is no goal, no purpose. There is just the relentless creative churn of evolution. But here is the thing, both frames can lead to the same place of humility and wonder. Whether you see the world as the intricate clockwork of a divine watchmaker or as the breathtaking, self-organizing dance of matter and energy, the result is a profound sense of awe at the complexity and beauty of it all. You can look at the feathered dinosaur we imagined, with its insulating coat adapted to the cold, and see it either as a piece of brilliant, intentional design or as a stunning example of emergent adaptation. The object of wonder is the same. Tonight, we do not need to choose between these frames. We can simply hold them side by side as two different ways of telling the story. They are both attempts by our human minds to grasp a reality that is ultimately larger than our language can contain. The humility comes from recognizing that whichever story we tell, we are still just scratching the surface of the mystery. And so where are you in all of this? We have journeyed across 66 million years, across shifting continents and changing climates. We have peered into the machinery of planets and the code of life. It is easy to feel like a distant spectator to this grand drama, but you are not. You are in the loop. The story of this planet is your story. The material that makes up your body was forged in the heart of stars. cycled through the oceans and the atmosphere of the Earth, and assembled by a genetic code that connects you in an unbroken chain to the very first life on this planet. You are a participant. Your breath is part of the carbon cycle. The water in your cells is part of the water cycle. Your choices, your actions, your very presence are woven into the fabric of the planetary system. This is not a metaphor. It is a physical reality. When you feel the warmth of the sun on your skin, you are feeling the energy that drives the entire biosphere. When you drink a glass of water, you're drinking the same water that has carved canyons and nourished forests for eons. This sense of personal belonging, of being located inside the system, is the ultimate gift of this kind of deep time exploration. It dissolves the illusion of separation. You are not a human being on the Earth. You are a part of the Earth, which is, for a brief and precious time, being human. This perspective brings with it a quiet sense of agency. Not the frantic agency of trying to control the world, but the grounded agency of a conscious participant. You are a part of the feedback loops. Your attention, your care, your understanding, these are inputs into the system. The way you see the world changes the way you act in the world, and the way you act in the world in small and subtle ways changes the world. By understanding the deep, interconnected story of our planet, whether it is our timeline or the one we have imagined tonight, we deepen our own sense of place. We realize that we belong to this story. It is not just a scientific narrative, it is our inheritance. It is our home. And that feeling of belonging deep in your bones is a source of profound calm and strength. Let's take a moment now to gently retrace our steps. We began tonight in the quiet of this room with a single, elegant question. What if the world of the dinosaurs had never ended? We set aside the moment of catastrophe and allowed the great river of Mesozoic life to flow onward into a new and unfamiliar Cenozoic era. We built this world not from fantasy but from the first principles of science. We looked at the co-evolutionary arms races that would have driven dinosaurs to new levels of sophistication. We zoomed out to see how their very existence would have shaped the planet's climate, creating feedback loops that might have kept the world warmer for longer. We listened to the slow celestial rhythm of the Earth and Moon, a cosmic clock that ticked on regardless of the life below. We explored the messy, resilient nature of the genetic code and the hard, physical constraints of the planet's energy budget. We saw how this world would have been a mosaic of the familiar and the strange, a world of smaller, faster, smarter dinosaurs adapting to a cooling planet. We confronted the objections to our model, acknowledged the deep uncertainties, and found a synthesis that was plausible, if not definitive. We translated these grand ideas into the lived reality of a single scene on a prehistoric beach, and into small, mindful practices for our own lives. And through it all, we journeyed from a simple "what if" to a deeper appreciation for the complex, interconnected, and resilient nature of life itself. We can now re-ask our core question, but with a new depth of understanding. What if the dinosaurs never went extinct? The answer is not a list of strange creatures. The answer is a different world. A planet with a different metabolism, a different rhythm, a different story written in its rocks and its air and its living inhabitants, a world whole and complete without us. And in imagining that world, we have perhaps come to understand our own a little better. As our time together comes to a close, I want to extend a quiet thank you. Thank you for lending your curiosity to this journey tonight. Thank you for being willing to let your mind drift into these deep, strange waters. In a world that so often demands quick answers and constant attention, the simple act of setting aside time for slow, gentle wondering is a precious thing. We are all part of a community of people who find solace and meaning in these kinds of explorations. If you feel so inclined, you are warmly invited to continue being a part of this space. But there is no urgency. The most important thing is that you have found a measure of calm, a moment of respite. Your presence here is what gives this shared exploration its meaning. So thank you simply for being here. May your curiosity continue to be a source of quiet joy in your life. Let the details of our imagined world now begin to soften and dissolve. Let the landscapes of the alternate Cenozoic fade like a dream upon waking. There is no need to hold on to any of it. The journey was the purpose, not the destination. The questions we've held are more important than any answers we might have found. They can remain, hanging in the quiet air, as gentle sparks of curiosity for another time. The tension of inquiry can now release. The mind can be allowed to float, untethered from the effort of thought and imagination. Return your awareness one last time to the simple, physical sensations of this moment. The feeling of your body being held, the gentle rise and fall of your chest, the temperature of the air on your skin. There is nothing left to figure out, nothing to solve. The great story of the Earth will continue whether we are watching it or not. The slow drift of the continents, the long cycles of the climate, the endless creative dance of evolution, these things will proceed at their own deep pace. And you can rest. You can release yourself into the great, quiet current of the night, knowing that you are a part of this immense and ongoing story. Let the last vestiges of thought drift away like clouds across the moon. All that remains is the stillness, the quiet, and the gentle pull of sleep. Curiosity has done its work for the night. Now it too can rest. The air in the room is still. It has a weight, a texture, a temperature that is unique to this moment, in this place. As you breathe in, you are breathing in the atmosphere of the Earth, an atmosphere that has been shaped by billions of years of geology and biology. It is an ocean of gas in which we live, connecting us all. The oxygen that fills your lungs was created by ancient sunlight captured by plants. The carbon dioxide you exhale will be taken up by a leaf on a tree, perhaps tomorrow, perhaps 100 years from now, to build its own body. This is the great cycle. The quiet landing of this documentary loops back to this single, profound point. You are not separate. The materials of the room around you, the wood, the cotton, the metal, all were drawn from the Earth's crust, processed by human hands, but ultimately they are of the planet, just like the bones of the dinosaurs we imagined, and just like your own bones. There is a continuity that runs through everything. As you drift now into sleep, perhaps you can feel that connection, the feeling of being a small, temporary, but beautiful expression of a very old, very large, and very mysterious system. The boundary between you and the world dissolves just for a moment, and in that quiet, boundless space there is only peace.